velvet darkness of our night sky lies a pattern of stars that ancient peoples called the Swan. This constellation, Cygnus, gracefully stretches its stellar wings across the summer heavens. But hidden within this celestial bird, among its twinkling feathers, lurks something extraordinary that cannot be seen by human eyes. This is the story of Cygnus X-1, one of the first black holes ever discovered and confirmed by science, a cosmic enigma that continues to whisper secrets about our universe from nearly 6,000 light-years away. When astronomers first detected this invisible giant in 1964, they could not have imagined how profoundly it would challenge our understanding of stellar evolution and cosmic physics. For this particular black hole, this devourer of light and matter, should not exist according to our earliest theories, and yet, it does. Tonight, as you rest and drift towards sleep, we will explore this cosmic paradox together. How a star died to create something both impossible and real. How scientists across generations worked to understand an object they could never directly see. And how Cygnus X-1 continues to shape our understanding of the most extreme objects in our universe. The black hole in the Swan sings a gravitational lullaby across light years, bending not just space-time, but the boundaries of human knowledge. Its existence reminds us that the cosmos often refuses our neat categories and predictions, that nature, in its infinite creativity, finds pathways we have yet to fully comprehend. Imagine now this dark heart beating in the distant sky, pulling matter from its companion star in a cosmic dance that has continued for millions of years. As we begin our journey into understanding this mysterious object, allow yourself to sink into the gentle gravity of curiosity and wonder. For in the story of Cygnus X-1, we find not just scientific discovery, but a testament to the beautiful strangeness of our universe. The Swan flies across our night sky, carrying within it a shadow that outshines understanding, a darkness that, paradoxically, has illuminated our cosmic knowledge, a black hole that should not exist, yet does. This is where our story begins. Look up, if you can, to the northern summer sky. Find the Northern Cross, as some call it. The bright star Deneb marks the tail of the Swan, while Albireo sits at its beak. Between them, spanning nearly 50 light-years of space, the body of Cygnus stretches across the Milky Way, and there, nestled within this cosmic bird, invisible to our eyes, Cygnus X-1 awaits. What makes this particular black hole so special? Why, among the millions that must exist in our galaxy alone, has this one captured the imagination of scientists for generations? The answer lies not just in its discovery, but in the beautiful contradiction of its existence. Black holes themselves were once considered mathematical curiosities, solutions to Einstein's equations that many physicists, including Einstein himself, thought too extreme to exist in nature. They were theoretical objects where gravity becomes so intense that not even light can escape. A region of space where known physics breaks down, where time itself warps beyond recognition. Cygnus X-1 changed everything. It transformed these mathematical abstractions into observable reality. Its discovery forced scientists to confront the existence of these cosmic extremes. And in the decades since, this particular black hole has continued to surprise us, challenging our most sophisticated models of how stars live and die. Across the electromagnetic spectrum, from radio waves to gamma rays, Cygnus X-1 reveals itself through its effects on the surrounding space, through its gravitational pull on its companion star, through the superheated matter that spirals toward its event horizon, the point of no return. As we explore this mysterious object together, we will journey through time as well as space, back to the 1960s, when rockets first carried X-ray detectors above Earth's atmosphere, through the debates and controversies of the 1970s, as evidence mounted that this strange source of radiation was indeed a black hole, to the present day, where sophisticated space telescopes continue to unveil new mysteries about this cosmic enigma. Cygnus X-1 teaches us humility before the cosmos. It reminds us that the universe often surpasses our imagination, that nature finds ways to create what our theories sometimes say cannot exist. In its paradoxical reality, we find a metaphor for scientific discovery itself, a journey of continuous wonder and revision. So close your eyes if you wish, and let your mind drift toward this distant point in space, where a star once shone brightly before collapsing into darkness, where matter now spirals into oblivion, releasing energy as it falls, where the boundary of knowledge meets the mystery of the unknown. This is Cygnus X-1, the black hole that should not exist, but does. Our story begins in the early 1960s, during a time of remarkable technological advancement and scientific ambition. The space age had dawned, and for the first time in human history, we could send instruments beyond the protective veil of Earth's atmosphere. This capability would prove transformative for astronomy, opening windows into wavelengths of light previously hidden from our view. One such window was the realm of X-rays. These energetic forms of light are completely absorbed by our atmosphere, a fortunate protection for life on Earth, but a frustrating limitation for astronomers. What secrets might the universe reveal when viewed through X-ray eyes? What cosmic phenomena might be discovered? Imagine, if you will, the night sky as seen by human eyes for countless generations, stars glittering like distant jewels, planets wandering among them, the misty band of the Milky Way stretching across the darkness, beautiful, certainly, but representing only a fraction of the light that the cosmos produces. Visible light is just a narrow band in the vast electromagnetic spectrum, which extends from long wavelength radio waves to extremely short wavelength gamma rays. For most of human history, we were blind to all but that narrow visible band. The advent of radio astronomy in the 1930s and 40s had already begun to expand our cosmic vision. Carl Jansky and Grote Reber had shown that the universe was speaking to us in radio waves, revealing features and phenomena invisible to optical telescopes. But at the other end of the spectrum, in the high-energy realm of X-rays and gamma rays, the universe remained silent to us, its messages blocked by our protective atmosphere. On June 12, 1962, a rocket launched from White Sands Missile Range in New Mexico. This was not a mission to place humans in space or deliver satellites to orbit. Instead, it carried sensitive instruments designed by a team led by physicist Riccardo Giacconi. The payload was modest, the flight time brief, just a few minutes above the atmosphere. Yet this fleeting glimpse of the X-ray sky would forever change our understanding of the cosmos. The technology aboard this rocket was revolutionary, yet remarkably simple in concept. It consisted of Geiger counters, which could detect incoming X-rays, shielded to block cosmic rays and other sources of interference. These detectors would scan across the sky as the rocket rotated during its short flight above the atmosphere. If cosmic sources of X-rays existed, the counters would register their presence. This mission was a gamble, based on theoretical predictions that some astronomical objects might emit X-rays. The Sun was known to produce X-rays, observed during rare solar eclipses when instruments could briefly peak above the atmosphere, but no one knew for certain whether more distant and powerful sources existed. Some scientists were skeptical, suggesting the mission might detect nothing at all. As the data from this pioneering mission was analyzed, the team made a startling discovery. They detected a powerful source of X-rays from a region in the constellation Scorpius, which they named Scorpius X-1. This was the first detection of an X-ray source beyond our solar system, and it immediately raised profound questions. What kind of cosmic object could produce such intense X-ray emissions? The intensity of this source was shocking. Scorpius X-1 was radiating energy in X-rays at a rate thousands of times greater than our Sun emits in all wavelengths combined. Yet optical telescopes showed nothing particularly unusual at that location, just an unremarkable star. Something extraordinary must be happening there, something that conventional astronomy had missed entirely. The success of this mission inspired a new generation of X-ray astronomy. In 1963, another rocket was launched, carrying more sensitive instruments. This time, additional sources were detected, including one from the direction of the Cygnus constellation. In 1964, this mysterious object received its designation, Cygnus X-1. At first, it appeared to be just another entry in the growing catalogue of cosmic X-ray sources. But as astronomers would learn over the following decade, this particular object would prove to be far more significant than initially realized. These early rocket flights, lasting just minutes above the atmosphere, could provide only tantalizing glimpses of the X-ray universe. Astronomers dreamed of longer observations, of instruments that could remain above the atmosphere for days or months rather than minutes. This dream began to be realized with the launch of the first dedicated X-ray astronomy satellite, Uhuru, on December 12, 1970. Uhuru, whose name means freedom in Swahili, was launched from a platform off the coast of Kenya on that country's Independence Day. This small satellite, weighing just 60 kilograms, carried instruments designed to survey the entire sky in X-rays. Over its 2-year operational lifetime, Uhuru would discover hundreds of X-ray sources and transform our understanding of the high-energy universe. Among the sources studied by Uhuru was Cygnus X-1. The satellite confirmed its presence and provided more detailed measurements of its X-ray output, but a fundamental limitation remained. Unlike visible light astronomy, with its centuries of star catalogues and precise positions, these early X-ray observations could only pinpoint sources to rather broad regions of the sky. Cygnus X-1 could be located only within an area several times larger than the full moon, as seen from Earth. Within that region, there were many visible stars. Which one, if any, might be connected to this powerful X-ray source? The challenge of connecting X-ray sources with objects visible in other wavelengths was a central problem of early X-ray astronomy. Without knowing what was producing these powerful emissions, astronomers could only speculate about their nature. Were they previously unknown types of stars, distant galaxies, something entirely new? The breakthrough for Cygnus X-1 came in 1971, 7 years after the initial discovery. Astronomer Louise Webster and her colleagues used a technique called lunar occultation to narrow down the position of Cygnus X-1. The Moon, in its orbit around Earth, occasionally passes in front of distant stars, briefly blocking their light. By carefully timing when the X-ray signal from Cygnus X-1 disappeared behind the Moon's edge, they could determine its position with much greater precision. This technique required precise timing and coordination. The team needed to know exactly when the Moon would pass in front of the region containing Cygnus X-1, and they needed an X-ray telescope observing at that exact moment. The observations had to be made from space, as the X-rays could not penetrate Earth's atmosphere. The logistics were daunting, but the potential scientific payoff enormous. When the data was analyzed, the results were clear. The position of Cygnus X-1 had been pinpointed with unprecedented accuracy. This improved position led to a remarkable correlation. Cygnus X-1 appeared to be in exactly the same location as a visible star catalogued as HDE 226868. This was no ordinary star, but a massive blue supergiant, approximately 30 times the mass of our Sun. Yet a blue supergiant alone should not produce such intense X-rays. Something else had to be present. Around the same time, radio astronomers made another crucial discovery. Using the technique of very long baseline interferometry, which combines radio telescopes separated by great distances to achieve extraordinary resolution, they detected a compact radio source at the exact same position. These converging lines of evidence painted an intriguing picture. The X-ray and radio emissions were coming from a system that included the visible blue supergiant star. But what was the source of these emissions? What invisible companion might be hiding in this system? To solve this mystery, astronomers turned to spectroscopy, the technique of splitting light into its component wavelengths. When applied to stars, spectroscopy can reveal their chemical composition, temperature, and, crucially, their motion toward or away from us. This motion creates a slight shift in the wavelengths of light, a phenomenon known as the Doppler effect, similar to how the pitch of a siren changes as an ambulance passes by. The answer began to emerge through the work of astronomers like Charles Bolton, who in 1971 published a groundbreaking study. By carefully analyzing the spectrum of the visible star, Bolton could measure its orbital motion. The blue supergiant appeared to be orbiting an unseen companion, completing one orbit every 5.6 days. This discovery was profound. The visible star was not stationary, but moving in a regular, predictable pattern. consistent with the gravitational influence of a massive companion. Yet no companion could be seen in optical telescopes. Whatever it was, it emitted no detectable visible light of its own. From the characteristics of this orbit, astronomers could calculate the mass of the invisible object. It had to be at least 6 times the mass of our Sun, possibly much more. This posed a profound puzzle, as no known type of object could be so massive yet completely invisible. To understand the significance of this mass estimate, we need to consider what happens to stars at the end of their lives. Stars like our Sun eventually become white dwarfs, dense remnants about the size of Earth but containing roughly the mass of the Sun. More massive stars can end as neutron stars, incredibly dense objects where a teaspoon of material would weigh billions of tons on Earth. Neutron stars, the collapsed cores of massive stars that had exploded as supernovae, typically have masses around 1.4 times that of our Sun. White dwarfs, another type of stellar remnant, cannot exceed about 1.4 solar masses without collapsing further. What could this invisible object be, with its mass of at least 6 suns? Theoretical physics provided a possible answer, but one so extreme that many scientists were reluctant to embrace it. In Einstein's theory of general relativity, if enough mass is concentrated in a small enough volume, the gravitational field becomes so intense that nothing, not even light, can escape. Such an object would form a boundary called an event horizon, beyond which events cannot affect an external observer. This theoretical construct had been given a name that captured its ominous nature: a black hole. The answer was as profound as it was unsettling. The only theoretical object that fit all the observations was a black hole, a concept that had emerged from Einstein's theory of general relativity, a region of space where gravity is so extreme that nothing, not even light, can escape, a cosmic sinkhole from which there is no return. But black holes at this time were still largely theoretical constructs, mathematical solutions to Einstein's equations that many physicists, including Einstein himself, considered too extreme to exist in reality. Some regarded them as mathematical curiosities rather than real astronomical objects. Yet here was compelling evidence for exactly such an object, hiding in plain sight within our galaxy. The term black hole itself was relatively new, coined by physicist John Wheeler in 1967. Before that, these objects were described with more technical terms like completely collapsed gravitational objects or frozen stars. Wheeler's evocative phrase captured the essential nature of these objects, making the concept more accessible to both scientists and the public. As the evidence accumulated throughout the early 1970s, a picture began to emerge of how this system functioned. The blue supergiant star and its black hole companion orbit a common center of mass. The intense gravity of the black hole pulls material from the outer atmosphere of the star. This material does not fall directly into the black hole, but instead forms a swirling disk around it, called an accretion disk. This process of matter transfer is not smooth or constant, but varies over time. Sometimes the flow increases, causing the accretion disk to brighten. Other times it decreases, and the X-ray emissions dim accordingly. This variability, observed in the X-ray output of Cygnus X-1, provided further evidence for the accretion disk model. As matter in this disk spirals closer to the black hole, it becomes heated to millions of degrees through friction and gravitational compression. At such extreme temperatures, the disk emits powerful X-rays, exactly what the orbital observatories had detected. The inner regions of this superheated disk occasionally launch jets of particles moving at nearly the speed of light, producing the radio emissions observed by radio telescopes. These jets are among the most energetic phenomena in the universe. They can extend for thousands of light years from their source, though in the case of Cygnus X-1, they are relatively modest. How exactly these jets form remains an area of active research even today, involving complex interactions between magnetic fields, rotating matter, and the intense gravitational field of the black hole. The discovery of Cygnus X-1 marked a turning point in our understanding of the universe. For the first time, astronomers had strong evidence for the existence of a black hole, not as a mathematical abstraction, but as a real object that could be studied through its effects on its surroundings. This discovery did not come easily or without controversy. Throughout the 1970s, alternative explanations were proposed and debated. Could the observations be explained by multiple neutron stars? Could our understanding of stellar masses be flawed? The scientific process demands skepticism, especially when confronted with extraordinary claims. One objection raised was that perhaps the visible star was itself unusual, with different properties than typical blue supergiants. If its mass had been underestimated, then the mass of its companion might also be lower than calculated, potentially bringing it into the range possible for neutron stars. Another suggestion was that perhaps the X-ray source was not directly associated with the visible star at all, but merely appeared to be in the same location due to a chance alignment. This possibility was gradually ruled out as more precise observations confirmed the association between the X-ray source and the visible star. One famous example of this healthy scientific debate involved the renowned physicist Stephen Hawking. In 1974, Hawking made a bet with fellow physicist Kip Thorne about the nature of Cygnus X-1. Hawking bet that it was not a black hole, while Thorne took the position that it was. This was not mere academic gamesmanship, but reflected genuine scientific uncertainty about what we were observing. The stakes of this bet were unusual. If Hawking lost, admitting that Cygnus X-1 was indeed a black hole, he would have to buy Thorne a one-year subscription to a magazine of private indulgences. If Thorne lost, acknowledging that Cygnus X-1 was not a black hole, he would have to buy Hawking a one-year subscription to a British political magazine. The asymmetry of these stakes reflected the different cultural backgrounds of the two physicists, one British and one American. Interestingly, Hawking later conceded this bet in 1990, as evidence for the black hole interpretation became overwhelming. He noted wryly that while he had lost the bet, the consolation prize was a better understanding of the universe. Such is the nature of science, where being proven wrong can be as valuable as being proven right, so long as it advances our knowledge. Hawking's concession was not merely a personal acknowledgement, but reflected the broader scientific consensus that had emerged. By the 1990s, the evidence for black holes, both in binary systems like Cygnus X-1 and at the centers of galaxies, had become overwhelming. What had once been controversial was now established science. The story of Cygnus X-1's discovery spans more than a decade, from those first rocket flights that detected cosmic X-ray sources to the complex, multi-wavelength observations that gradually revealed its true nature. It is a testament to human ingenuity and persistence, to our ability to detect and decipher signals from objects thousands of light years away. This journey of discovery also reminds us of the collaborative nature of science. No single observation or theorist provided the complete picture. Instead, it emerged through the combined efforts of X-ray astronomers, optical astronomers, radio astronomers, and theoretical physicists, each contributing pieces to the puzzle. Consider the diverse techniques and instruments involved in unveiling Cygnus X-1. Rocket-borne and satellite X-ray detectors revealed its high-energy emissions. Optical telescopes studied its visible companion star. Radio telescopes detected its jets. Spectroscopic analysis revealed the orbit and masses of the components. Theoretical physics provided the framework to interpret these observations. Each approach had limitations, but together, they created a compelling and coherent picture. The instruments used to study Cygnus X-1 also evolved rapidly during this period. From those first brief rocket flights, astronomical X-ray detection advanced to dedicated satellite observatories like Uhuru, launched in 1970, which provided the first comprehensive survey of the X-ray sky. Radio astronomy underwent a similar revolution, with new techniques allowing unprecedented resolution and sensitivity. Throughout the 1970s, each new observation refined our understanding of this remarkable system. The mass of the invisible companion was initially estimated at about 6 solar masses, but was later revised upward. Modern estimates place it at about 21 solar masses, more than 21 times the mass of our Sun. The visible star, HDE 226868, is even more massive, at approximately 40 times the Sun's mass. Together, they form one of the most massive binary star systems known in our galaxy. The discovery also sparked interest in the broader question of how such systems form. The standard model of stellar evolution suggests that massive stars end their lives as supernovae, catastrophic explosions that can disrupt binary systems. How then did this system remain intact? The answer likely involves complex interactions between the two stars during their evolution, perhaps including phases where they exchanged mass before one collapsed to form a black hole. By the end of the 1970s, the evidence was overwhelming. Cygnus X-1 was indeed a black hole, orbiting in a deadly dance with its stellar companion. This conclusion opened a new chapter in astronomy. If one such object existed in our galaxy, surely there must be others. A new class of astronomical objects, binary systems containing black holes, entered the scientific lexicon. These systems became known as X-ray binaries, with Cygnus X-1 as their prototype. Over the following decades, dozens more would be discovered, each with its own variations and peculiarities, but all sharing the basic structure first revealed in Cygnus X-1. A normal star orbiting with a compact object, transferring matter that heats up and emits X-rays as it spirals toward the event horizon. The significance of Cygnus X-1 extends beyond its role as the first confirmed black hole. It also serves as a laboratory for studying extreme physics under conditions impossible to recreate on Earth. The matter in the accretion disk experiences temperatures of millions of degrees and intense gravitational and magnetic fields. By studying the X-ray emissions from this system, astronomers can test theories about how matter behaves under these extreme conditions. The discovery of Cygnus X-1 illustrates how science often advances, not through sudden, dramatic revelations, but through the patient accumulation of evidence, the testing of hypotheses, the development of new technologies, and the courage to follow where the data leads, even when it points to something as extreme and counterintuitive as a black hole. As we lie here, contemplating this cosmic wonder, remember that the light from the visible star in this system, HDE 226868, has traveled approximately 6,000 light-years to reach our eyes. This means we are seeing this star as it existed 6,000 years ago, when human civilization was just beginning to develop writing systems, when the Great Pyramids of Egypt were still in the future. Yet the blue supergiant we observe is likely still there, still locked in its fateful orbit with its dark companion, still feeding matter into the cosmic whirlpool that is Cygnus X-1. This cosmic dance will continue long after our brief human lives have ended, a reminder of the immense scales of space and time across which cosmic dramas unfold. And now, as we delve deeper into the nature of this remarkable system, we will explore not just what Cygnus X-1 is, but why its very existence poses profound challenges to our understanding of stellar evolution and the birth of black holes. For this particular black hole, this first confirmed specimen of the most extreme objects in the universe should not exist according to our earliest models. And yet, against theoretical expectations, it does. For centuries, humans have gazed at the night sky, cataloging stars, watching planets wander across the heavens, pondering our place in this vast universe. But nothing in those centuries of observation had prepared astronomers for what they found in Cygnus X-1, an object invisible to the eye, detectable only through its gravitational influence and the energetic radiation produced as it devours its stellar companion. An object that challenges our intuitions about the nature of space, time, and matter. A black hole. But what exactly is a black hole? To understand this strange cosmic entity and appreciate why the discovery of Cygnus X-1 was so momentous, we need to journey through the history of an idea. For black holes existed in the human mind, long before we found evidence of them in the heavens. The concept has its origins in the late 18th century, when a British natural philosopher named John Michell considered a thought experiment. What if there existed a star so massive that light itself could not escape its gravitational pull? Michell, working with Newtonian physics and the then new understanding that light had a finite speed, calculated that a star 500 times the size of our Sun would have a gravitational pull so strong that light could not escape from its surface. Michell called such an object a dark star. He suggested that while we could not see such objects directly, we might detect them through their gravitational effects on visible stars. This remarkably prescient idea, published in 1783, anticipated by nearly 2 centuries how we would eventually discover real black holes like Cygnus X-1. A similar idea was independently developed by French mathematician Pierre-Simon Laplace in 1796. Like Michell, Laplace recognized that sufficiently massive objects might trap light. Both men were working with Newtonian concepts of gravity and light that would later be superseded, but their insights pointed toward a profound truth about our universe. The modern theoretical understanding of black holes emerged from Albert Einstein's general theory of relativity, published in 1915. This revolutionary theory reimagined gravity not as a force acting across space, as Newton had conceived it, but as a curvature of space-time itself. Massive objects like stars and planets bend the fabric of space-time, and this curvature guides the motion of other objects. Just weeks after Einstein published his equations, German physicist Karl Schwarzschild found a solution to them that described the space-time around a perfectly spherical mass. Working from a field hospital during World War I, Schwarzschild discovered something remarkable. If a mass is concentrated into a small enough volume, the curvature of space-time becomes infinite at a certain distance from the center. This boundary would later become known as the event horizon. Schwarzschild's solution contained a mathematical singularity, a point where the equations break down and physical quantities become infinite. Such singularities often indicate that a theory has been pushed beyond its limits of applicability. For this reason, Einstein and many other physicists initially believed that Schwarzschild's solution was a mathematical curiosity rather than a description of something that could exist in the real universe. For decades, this view prevailed. The idea that a star could collapse to form such an extreme object seemed too fantastic. Various arguments were advanced for why nature would prevent such a collapse. Perhaps pressure from subatomic particles would halt the contraction. Perhaps some yet unknown physics would intervene. The term black hole itself did not exist in these early discussions. Oppenheimer and his colleagues referred to frozen stars because, according to their calculations, time would appear to slow and ultimately stop for an outside observer watching a star collapse. Others used phrases like completely collapsed gravitational objects, or simply collapsed stars. The more evocative and now ubiquitous term black hole was popularized by American physicist John Wheeler in 1967. The name captures the essential nature of these objects: black because no light escapes, a hole because matter can fall in but cannot return. Wheeler's terminology helped make the concept more accessible and sparked greater interest both within the scientific community and among the public. The modern theoretical understanding of black holes developed primarily between the 1930s and 1960s. In 1939, Robert Oppenheimer and Hartland Snyder published a paper demonstrating that, according to general relativity, sufficiently massive stars would indeed collapse under their own gravity once they exhausted their nuclear fuel. Nothing could halt this collapse, and the star would shrink to a point of infinite density, a singularity. Meanwhile, astronomers had been discovering increasingly bizarre objects in the cosmos. Supernovae, the explosive deaths of massive stars, had been observed for centuries, but their nature was only beginning to be understood. Neutron stars, incredibly dense remnants of stellar explosions, were predicted in the 1930s, but not confirmed observationally until 1967, when pulsars, rapidly rotating neutron stars, emitting beams of radiation, were discovered by Jocelyn Bell Burnell and Anthony Hewish. These discoveries prepared the intellectual ground for considering even more extreme objects. If neutron stars existed, with densities so great that a teaspoon of their material would weigh billions of tons on Earth, perhaps the even more extreme black holes predicted by general relativity might also be real. Yet, doubt persisted. Some physicists argued that the singularities predicted by general relativity indicated a flaw in the theory rather than a feature of reality. Others suggested that some yet undiscovered law of physics might prevent the formation of event horizons. The debate was not merely academic, but touched on fundamental questions about the nature of space, time, and physical law. By the mid-20th century, the theoretical groundwork for understanding black holes was largely complete. What remained was to determine whether such objects actually existed in our universe or were merely mathematical curiosities. This was the state of knowledge when the first celestial X-ray sources were detected in the early 1960s. The significance of Cygnus X-1 was not immediately recognized. When it was first detected in 1964, it was simply catalogued as another X-ray source. Only as more data accumulated, particularly regarding the mass of the invisible companion to HDE 226868, did the possibility emerge that astronomers were observing a black hole. The news that Cygnus X-1 might be a black hole generated tremendous excitement in the scientific community. If confirmed, it would vindicate decades of theoretical work and open a new chapter in our understanding of the universe. But scientists are cautious by nature, especially when confronting extraordinary claims. Alternative explanations were actively sought and debated. Could the invisible companion be a neutron star instead? This seemed unlikely given its calculated mass of at least 6 solar masses, far above the theoretical maximum for neutron stars. Could it be a cluster of neutron stars? This would require a remarkably stable configuration that seemed improbable. Could it be some yet unknown type of object? Possibly, but invoking an unknown object, when a known theoretical prediction fits the observations, violates the principle of parsimony, also known as Occam's razor. As observations improved through the 1970s, the case for Cygnus X-1 being a black hole strengthened. More precise measurements of the orbital parameters of the visible star allowed for better mass estimates of its invisible companion. The calculated mass consistently exceeded the theoretical maximum for neutron stars, typically considered to be about 3 solar masses. The behavior of the X-ray emissions from Cygnus X-1 also matched theoretical predictions for matter falling into a black hole. The accretion disk, a swirling vortex of gas stripped from the visible star and spiraling toward the event horizon, would heat to millions of degrees through friction and gravitational compression. This superheated gas would emit X-rays with specific characteristics, consistent with what was observed. Rapid fluctuations in the X-ray output, occurring on timescales of milliseconds, indicated that the emission region must be very small, consistent with an accretion disk surrounding a compact object like a black hole. The spectrum of the X-rays, the distribution of their energies, also matched theoretical models of black hole accretion disks. By the late 1970s, most astronomers accepted that Cygnus X-1 contained a black hole. In 1971, the prominent astrophysicist Stephen Hawking had arranged his bet with Kip Thorne, wagering that Cygnus X-1 was not a black hole. By 1990, the evidence had become so compelling that Hawking conceded the bet. This concession, from one of the world's foremost authorities on black hole theory, symbolically marked the transition of black holes from theoretical construct to observed reality. Yet uncertainties remained. The exact mass of the black hole in Cygnus X-1 has been revised several times as measurement techniques improved. Initial estimates placed it at about 6 to 9 solar masses. By 2010, more precise measurements suggested a mass of about 14.8 solar masses. More recent estimates, from around 2020, place it at about 21 solar masses. These revisions reflect the inherent difficulties in making precise astronomical measurements, as well as advancements in methodology. Each new estimate has strengthened the case for a black hole, as the mass has consistently been revised upward, well beyond what could be explained by any known type of object other than a black hole. The confirmation of Cygnus X-1 as a black hole opened the floodgates for discovering more of these extreme objects. Throughout the 1980s and 1990s, additional X-ray binaries were identified as likely containing black holes. These systems shared key characteristics with Cygnus X-1, including intense X-ray emissions, evidence for accretion disks, and invisible companions with masses too great to be neutron stars. Among these newly discovered systems were A0620, which contains a black hole of around 12 solar masses, and GRS 1915+105, with a black hole of about 12 to 15 solar masses. Each new discovery reinforced the reality of black holes and provided additional laboratories for studying these extreme objects. The discovery of black holes in binary systems was just the beginning. Astronomers began to find evidence for supermassive black holes, millions or billions of times more massive than our Sun, at the centers of galaxies. The first strong evidence came from observations of the galaxy M87, which showed signs of a black hole of about 3.5 billion solar masses. Our own Milky Way galaxy harbors a supermassive black hole at its center, now known as Sagittarius A star. With a mass of about 4 million suns, this black hole is currently dormant, emitting relatively little radiation compared to active galactic nuclei in other galaxies. But it has shaped the evolution of our galaxy and continues to influence the motion of stars in the galactic center. The relationship between stellar mass black holes like Cygnus X-1 and these supermassive monsters remains an area of active research. Do supermassive black holes form from the mergers of many stellar black holes? Do they grow primarily by accreting gas from their surroundings? Did some form directly from the collapse of enormous clouds of gas in the early universe? The answers to these questions are still being sought. In recent years, an intermediate class of black holes, with masses of hundreds to thousands of solar masses, has been detected. These intermediate mass black holes may represent an evolutionary link between stellar and supermassive black holes, though their formation mechanisms are still debated. The story of black hole discovery took another dramatic turn in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from the merger of two black holes. This detection not only provided direct evidence for the existence of gravitational waves, confirming another prediction of Einstein's general relativity, but also demonstrated a new method for observing black holes. Unlike traditional astronomical observations, which rely on electromagnetic radiation, such as light or radio waves, gravitational wave observatories detect ripples in space-time itself. These ripples are produced by extreme events, such as the spiraling together and merger of two black holes. The pattern of the gravitational waves provides information about the masses of the black holes and their orbital dynamics. Since that first detection, dozens of black hole mergers have been observed through gravitational waves. These observations have revealed a population of black holes in the 30 to 100 solar mass range, somewhat heavier than those typically found in X-ray binaries like Cygnus X-1. This suggests that our understanding of black hole formation and evolution is still incomplete. Another breakthrough came in 2019, when the Event Horizon Telescope, a global network of radio telescopes linked to function as a single Earth-sized instrument, captured the first image of a black hole's shadow. The subject was the supermassive black hole at the center of galaxy M87, the same one that had provided early evidence for supermassive black holes. The image shows a bright ring of hot gas surrounding a dark central region, the shadow cast by the black hole against the bright background. This shadow is about 2.5 times larger than the event horizon itself, due to the way the black hole bends light around it. This direct visual evidence further confirmed our theoretical understanding of black holes. The black hole in Cygnus X-1 is too small and too far away for current technology to image directly in this way. But as the progenitor, the first confirmed black hole, it holds a special place in the history of astronomy. It was the bridge between theoretical prediction and observable reality, the object that transformed black holes from mathematical abstractions to concrete astrophysical entities. The journey from Mitchell's 18th century thought experiment to the modern understanding of black holes spans more than 2 centuries of human inquiry. It encompasses advances in physics, from Newtonian mechanics to general relativity and quantum theory. It involves the development of new observational techniques and technologies, from optical telescopes to X-ray satellites to gravitational wave detectors. And at its heart is the human drive to understand the most extreme phenomena in our universe. Black holes challenge our intuitions about the nature of reality. They represent regions where the familiar rules of physics break down, where space and time behave in ways that defy everyday experience. At the center of a black hole, according to current theory, lies a singularity, a point of infinite density where general relativity itself fails. Understanding what happens at such singularities will require a quantum theory of gravity, a unification of general relativity with quantum mechanics that remains one of the greatest outstanding challenges in theoretical physics. Despite these profound theoretical challenges, black holes are now accepted as common features of our universe. Most large galaxies are believed to harbor supermassive black holes at their centers. Stellar mass black holes are the end states of massive stars, scattered throughout galaxies like our own. Far from being rare or exotic, black holes are fundamental components of the cosmic landscape. The confirmation of Cygnus X-1 as a black hole was a watershed moment in this journey of discovery. It transformed black holes from theoretical possibilities to observable realities. It vindicated decades of theoretical work and opened new avenues for exploring the most extreme environments in the cosmos. And it reminded us that the universe is often stranger and more marvelous than we can imagine. As we drift towards sleep, contemplating the dark companion of HDE 226868, we can appreciate the remarkable fact that a concept that began as a mathematical curiosity a solution to equations that many thought too extreme to represent reality, turned out to be an actual feature of our universe. Cygnus X-1, the first confirmed black hole, stands as a monument to human curiosity, ingenuity, and the enduring quest to understand the cosmos. And yet, as we will explore in subsequent chapters, this particular black hole still holds mysteries. Its very existence challenges our models of stellar evolution and black hole formation. Its properties, from its mass to its rapid rotation, continue to surprise astronomers. Cygnus X-1 may have been the first black hole discovered, but it has not yet revealed all its secrets. Before we proceed, let us reflect on the truly wondrous nature of what we are discussing. Somewhere, in the constellation of the Swan, about 6,000 light-years from Earth, there exists an object so dense that a teaspoon of its material would weigh as much as all of humanity. An object whose gravitational pull is so extreme that not even light can escape from within its event horizon. An object that warps space-time so severely that our ordinary concepts of space and time lose meaning. This is not science fiction, but scientific fact, established through careful observation, rigorous analysis, and theoretical insight. Cygnus X-1 reminds us that truth is often stranger than fiction, that the universe contains wonders beyond our wildest imagination. And it all began with a strange source of X-rays, detected by instruments carried briefly above our atmosphere by rockets launched from the New Mexico desert. In the next chapter, we will delve deeper into what makes Cygnus X-1 unique among black holes, why its particular characteristics continue to challenge our understanding, and what it might tell us about the life cycles of stars and the formation of these cosmic singularities. But for now, let the thought of this invisible giant, silently pulling matter from its stellar companion, serve as a reminder of the beautiful strangeness of our universe and the joy of scientific discovery. Cygnus X-1, the first confirmed black hole, a cosmic enigma that changed our view of the universe forever. In the quiet depths of space, approximately 6,000 light-years from Earth, Cygnus X-1 continues its cosmic dance with its stellar companion. This black hole, the first ever confirmed, has been studied for decades since its discovery in the 1960s. Yet even now, it continues to challenge our understanding of stellar evolution and black hole formation. What makes this particular black hole so strange, so puzzling to astronomers and astrophysicists? Why does Cygnus X-1 stand out among the growing catalogue of known black holes? To understand the mysteries of Cygnus X-1, we must first consider what we know about this remarkable system. Modern measurements have refined our understanding of its basic parameters. The black hole itself has a mass of approximately 21 solar masses, meaning it contains the mass of 21 suns compressed into a region smaller than Manhattan. Its companion, the blue supergiant star HDE 226868, is even more massive, at about 40 solar masses. Together, they form one of the most massive binary star systems in our galaxy. The two objects orbit their common center of mass every 5.6 days, an incredibly rapid pace for such massive celestial bodies. For comparison, Mercury, the innermost planet in our solar system, takes 88 days to orbit the Sun. The black hole and its companion are separated by an average distance of about 0.2 astronomical units, or about 20% of the distance between Earth and the Sun. At this close proximity, the intense gravitational field of the black hole pulls matter from the outer atmosphere of the blue supergiant. This material forms a swirling accretion disk around the black hole, heating to millions of degrees as it spirals inward. The superheated gas emits powerful X-rays, which is how Cygnus X-1 was first detected. These basic facts about Cygnus X-1 are well established, but it is the implications of these facts, particularly regarding how this system formed and evolved, that continue to perplex astronomers. The first and perhaps most significant puzzle is the mass of the black hole itself. At 21 solar masses, Cygnus X-1 is significantly more massive than many stellar mass black holes found in our galaxy. While this might not seem surprising, given that black holes are formed from the collapsed cores of massive stars, it creates a theoretical challenge. According to our understanding of stellar evolution, stars in our galaxy with the metallicity of Cygnus X-1's progenitor, that is, the abundance of elements heavier than helium, should lose much of their mass through stellar winds before collapsing to form black holes. Metallicity plays a crucial role in stellar evolution. In astronomical terms, all elements heavier than helium are considered metals. These elements, such as carbon, oxygen, and iron, were forged in the hearts of previous generations of stars and scattered through space when those stars exploded as supernovae. New stars form from clouds of gas enriched with these heavier elements. Stars with higher metallicity, like those in the disk of our Milky Way galaxy, experience stronger stellar winds. These winds are streams of particles ejected from the star's outer layers, driven by the pressure of the star's radiation. Higher metallicity means more atoms with complex electron structures that can absorb radiation more efficiently, leading to stronger winds and greater mass loss over the star's lifetime. According to theoretical models, a star in our galaxy with the initial mass needed to produce a black hole should lose so much mass through these winds that the resulting black hole would be significantly less massive than what we observe in Cygnus X-1. The star that collapsed to form this black hole must have retained much more of its initial mass than our models predict. This discrepancy suggests that either our understanding of stellar winds and mass loss is incomplete, or the black hole in Cygnus X-1 formed through some unusual process. Perhaps the progenitor star had lower metallicity than typical for our galaxy, leading to weaker stellar winds and less mass loss. Or perhaps the presence of the companion star somehow affected the evolution of the black hole progenitor, allowing it to retain more of its mass. To appreciate the magnitude of this puzzle, consider the typical life cycle of a massive star. Stars with initial masses above about 8 solar masses are destined to end their lives in dramatic fashion. After burning through their hydrogen fuel in a few million years, these stars progress through a series of nuclear fusion stages, burning helium, then carbon, oxygen, and heavier elements, until they develop an iron core. Iron represents a nuclear dead end, as fusing iron atoms consumes rather than releases energy. When the iron core grows to about 1.4 solar masses, it can no longer support itself against gravity and collapses catastrophically. This collapse launches a shock wave that, in typical cases, expels the star's outer layers in a supernova explosion, while the core collapses to form either a neutron star or, if massive enough, a black hole. For stars in our galaxy, with its relatively high metallicity, stellar winds are expected to strip away much of the star's mass before this final collapse. A star might begin with 40 or 50 solar masses but end up with 15 to 20 solar masses by the time it exhausts its nuclear fuel. After the supernova explosion ejects additional mass, the resulting black hole should be even less massive, perhaps around 5 to 10 solar masses. Yet Cygnus X-1's black hole has a mass of 21 solar masses, significantly higher than predicted by this standard scenario. This suggests that the progenitor star must have retained more of its mass than our models predict, or that the black hole gained significant mass after its formation, perhaps by accreting matter from its companion. The second major puzzle of Cygnus X-1 concerns its formation. When a massive star exhausts its nuclear fuel, its core collapses, while its outer layers are expelled in a supernova explosion. This explosion is typically violent enough to disrupt a binary system, either sending the two stars on separate trajectories or, at minimum, significantly altering their orbit. Yet Cygnus X-1 appears to have a relatively stable, circular orbit with its companion star. This suggests that either the black hole formed without a powerful supernova explosion, or the binary system somehow survived such an explosion intact. Both scenarios challenge our current understanding of how massive stars end their lives and how black holes form. One possibility is that the black hole formed through a process called direct collapse, where the core of the massive star collapses directly to a black hole without a significant supernova explosion. This scenario might occur if the star is so massive that the collapsing core triggers the formation of a black hole before the shock wave that would normally cause a supernova can develop. In this direct collapse scenario, the enormous gravitational pull of the newly formed black hole might capture much of the material that would otherwise have been ejected in a supernova. This would help explain the high mass of the black hole. It would also explain why the binary system remained intact, as there would have been no powerful explosion to disrupt it. Another possibility is that the progenitor star lost its outer layers more gradually, perhaps through interaction with its companion, before the core collapsed to form a black hole. This would be a less violent process than a typical supernova and might allow the binary system to remain intact. In this scenario, the two stars in the system would have evolved in close proximity, with the more massive star, the progenitor of the black hole, expanding as it evolved and transferring mass to its companion. This mass transfer could have stripped away the outer layers of the progenitor star in a controlled manner without the violent explosion of a typical supernova. Such mass transfer is known to occur in close binary systems and can significantly alter the evolutionary paths of both stars. It might explain several peculiarities of Cygnus X-1, including the high mass of the companion star, which could have gained material from the black hole progenitor. A third possibility is that the system did experience a supernova, but it was what astronomers call an asymmetric or kicked supernova, where the explosion imparts momentum in just the right direction to maintain the binary configuration, albeit with a modified orbit. This would require a remarkable coincidence, but in the vastness of our galaxy, even rare events occur. In this scenario, the explosion would have been asymmetric, with more material ejected in one direction than others. This asymmetry would have given the collapsing core a kick in the opposite direction, potentially in just the right way to maintain its orbit around the companion star. While this seems like an improbable fine-tuning, the universe is vast, and we might be observing Cygnus X-1 precisely because it is one of the rare systems where such fine-tuning occurred. The third enigma of Cygnus X-1 is its spin. Black holes are characterized not only by their mass, but also by their angular momentum, or spin. According to measurements made using X-ray observations, the black hole in Cygnus X-1 is spinning very rapidly, close to the maximum rate allowed by general relativity. This rapid spin is challenging to explain given our current understanding of black hole formation. If the black hole formed from the collapse of a slowly rotating stellar core, it should not be spinning so quickly. The spin could have been acquired after formation through the accretion of matter from its companion star. But calculations suggest that the amount of matter accreted over the lifetime of Cygnus X-1 is insufficient to spin up the black hole to the observed rate. The spin of a black hole is measured by a parameter called A, which ranges from 0 for a non-rotating black hole to 1 for a maximally rotating black hole. Recent measurements suggest that the spin parameter of Cygnus X-1's black hole is greater than 0.95, extremely close to the maximum possible value. Such rapid rotation has profound effects on the spacetime around the black hole. It drags the fabric of spacetime around it, a phenomenon known as frame dragging or the Lentz-Thirring effect. This creates a region around the black hole called the ergosphere, where nothing can remain stationary with respect to distant observers, not even light. The rapid spin also affects the inner edge of the accretion disk. For a non-rotating black hole, the innermost stable circular orbit, the closest an object can orbit without inevitably falling in, is at 3 times the Schwarzschild radius, the radius of the event horizon. But for a rapidly rotating black hole, this innermost stable orbit moves much closer to the event horizon, allowing matter to extract more energy before plunging into the black hole. This proximity to the event horizon means that the accreting matter in Cygnus X-1 reaches higher temperatures and velocities before disappearing from our universe. The X-ray emissions from this system are therefore more energetic and variable than they would be for a slowly rotating black hole of the same mass. Another possibility is that the black hole inherited its spin from the rapidly rotating core of its progenitor star. But this raises questions about how the core could have maintained such rapid rotation during the late stages of stellar evolution, when various processes tend to slow stellar rotation. Stars naturally rotate, with young stars typically spinning more rapidly than older ones. Over time, processes like stellar winds and the expansion of the star's outer layers as it evolves tend to slow this rotation, transferring angular momentum from the star to its surroundings. By the time a massive star reaches the end of its life, its rotation rate has usually decreased significantly. However, the core of the star can, under certain conditions, maintain a rapid rotation, even as the outer layers slow down. This is especially true if the star is in a close binary system, where tidal interactions with the companion can affect the star's rotation. If the progenitor of Cygnus X-1's black hole was indeed in a close binary configuration with its current companion, which seems likely, these tidal interactions might have played a crucial role in maintaining the rapid rotation of its core. When this core eventually collapsed to form a black hole, it could have retained this rapid rotation, explaining the high spin observed today. The mysteries deepen when we consider the age and evolutionary state of the Cygnus X-1 system. The companion star, HDE 226868, is a massive blue supergiant, a star in an advanced stage of evolution. Based on its properties, astronomers estimate that this star is only a few million years old. This is extremely young by stellar standards. Our Sun, for comparison, is about 4.5 billion years old. Given the young age of the companion star, the black hole must also have formed relatively recently, but this creates a timing puzzle. The progenitor of the black hole, being more massive than the companion, should have evolved more quickly and reached the end of its life sooner. Yet it appears that the black hole formed and the companion star evolved to its current state within a very tight time frame. Massive stars evolve much more quickly than smaller stars like our Sun. A star with 40 solar masses, similar to the companion in Cygnus X-1, will exhaust its hydrogen fuel and begin to evolve off the main sequence in just a few million years. A star of 60 or 70 solar masses, which might have been the progenitor of the black hole, would evolve even more quickly, perhaps in as little as 2 to 3 million years. This suggests complex interactions between the two stars during their evolution. Perhaps they exchanged mass, with the progenitor of the black hole transferring material to the companion, thus extending its own life while accelerating the evolution of the companion. Or perhaps both stars formed with very similar masses, leading to nearly synchronized evolution until one collapsed to form a black hole. Mass transfer in binary systems can indeed create such evolutionary complexity. If the progenitor of the black hole began transferring mass to its companion as it expanded during its evolution, it would have slowed its own evolutionary progress while accelerating that of its companion. This could explain why the companion star, despite its high mass, is still present and has not yet exploded as a supernova itself. Yet another mystery of Cygnus X-1 concerns its location and motion within our galaxy. Recent measurements have shown that the system is moving through space at a relatively high velocity compared to neighboring stars. This suggests that it received a kick at some point in its history, possibly from the supernova explosion that formed the black hole. The system is moving at approximately 100 kilometers per second relative to its surroundings, a significant velocity for such massive objects. This motion is not aligned with the general rotation of the galaxy, indicating that it is the result of some event specific to Cygnus X-1, rather than just the natural orbital motion of stars around the galactic center. If this velocity is indeed the result of a kick from a supernova explosion, it suggests that the formation of the black hole was not as smooth and direct as some theories propose. There must have been at least some asymmetric explosion or ejection of material to impart this momentum to the system. But if a powerful enough supernova occurred to give the system this velocity kick, how did the binary survive intact? This brings us back to the formation puzzle and suggests that the birth of this black hole was even more complex than we might have imagined. Perhaps the explosion was asymmetric in just the right way to impart a velocity to the system as a whole while not disrupting the binary orbit. Or perhaps the kick came not from a supernova, but from gravitational interactions with other stars or gas clouds during the system's journey through the galaxy. These interactions would have been subtle, occurring over millions of years, slowly altering the system's trajectory without disrupting its internal dynamics. Adding to the intrigue is the distance of Cygnus X-1 from Earth. For many years, its distance was estimated at about 6,000 light-years. But more recent measurements using parallax, a technique that measures the apparent shift in position of an object when viewed from different points in Earth's orbit around the Sun, suggest a distance closer to 8,000 light-years. This revision in distance affects all other parameters of the system, including the masses of the black hole and its companion, their separation, and the amount of energy being released. It's a reminder of the ongoing refinement in our understanding of this system and the challenges of making precise astronomical measurements. The peculiarities of Cygnus X-1 extend beyond its basic parameters to its behavior. Like many X-ray binaries, it exhibits variability in its emission. The X-ray output can change on timescales ranging from milliseconds to months. These variations provide clues about the processes occurring near the black hole's event horizon, where matter is heated to extreme temperatures before disappearing forever. On the shortest timescales, milliseconds to seconds, the X-ray emission can flicker rapidly. These flickerings, or quasi-periodic oscillations, are thought to arise from processes in the innermost regions of the accretion disk, where material orbits the black hole at a significant fraction of the speed of light. The precise mechanism behind these oscillations remains an area of active research. Some theories suggest that these rapid oscillations are related to orbital motions in the innermost parts of the accretion disk. Others propose that they arise from resonances or waves in the disk. Still, others link them to interactions between the disk and the black hole's magnetic field, which is dragged and twisted by the black hole's rotation. These oscillations are not unique to Cygnus X-1 but have been observed in many X-ray binary systems. What makes Cygnus X-1 special is the combination of its high mass, rapid spin, and the detailed observations available due to its brightness and historical significance. These factors make it an ideal laboratory for studying these oscillations and testing theories about accretion processes near black holes. On longer timescales, hours to days, the X-ray emission can vary due to changes in the rate at which matter flows from the companion star to the black hole. These variations might be related to the orbital motion of the binary, or to instabilities in the companion star's atmosphere. As the two objects orbit their common center of mass, the tidal forces exerted by the black hole on the companion star vary slightly due to the eccentricity of the orbit. These varying forces can cause fluctuations in the rate at which material is stripped from the companion's atmosphere. More material means more accretion, which leads to brighter X-ray emission. Additionally, the companion star itself is not static. Like all stars, it can experience fluctuations in its output and structure. These variations, while subtle compared to the dramatic processes occurring near the black hole, can nevertheless affect the rate of mass transfer and thus the X-ray emission. On the longest timescales, weeks to years, Cygnus X-1 can transition between different emission states. In the hard state, it emits mostly high-energy X-rays and launches powerful jets of particles moving at nearly the speed of light. In the soft state, it emits mostly lower-energy X-rays, and the jets are suppressed. These state transitions reflect changes in the structure of the accretion disk and the environment immediately surrounding the black hole. These state transitions are among the most puzzling aspects of black hole binaries, like Cygnus X-1. They involve complex changes in the accretion flow, the radiation processes, and the jet formation mechanism. Understanding these transitions requires modeling all these processes and their interactions, a formidable theoretical challenge. Current theories suggest that in the hard state, the accretion disk is truncated at some distance from the black hole, with the inner region replaced by a hot, diffuse flow. This hot flow is less efficient at radiating energy, which leads to higher temperatures and harder X-ray emission. It is also conducive to jet formation, possibly through interactions with the black hole's magnetic field. In the soft state, the accretion disk extends closer to the black hole. This configuration is more efficient at radiating energy, leading to cooler temperatures and softer X-ray emission. The closer proximity of the disk to the black hole somehow suppresses jet formation, though the exact mechanism remains unclear. The jets themselves are another fascinating aspect of Cygnus X-1. These narrow beams of particles, primarily electrons and positrons, are accelerated to velocities approaching the speed of light and can extend for light years from the black hole. The energy required to launch these jets is enormous, and the mechanism by which they are produced involves complex interactions between the black hole's gravity, the accreting matter, and magnetic fields. Recent observations have revealed that these jets may be more powerful than previously thought. They interact with the interstellar medium, creating shock waves and heating the surrounding gas. This interaction creates a kind of cosmic feedback, where the black hole's activity affects its environment, which in turn can influence the future accretion onto the black hole. This feedback process is not unique to Cygnus X-1, but is observed in many accreting systems, from stellar mass black holes to the supermassive black holes at the centers of galaxies. It plays a crucial role in regulating star formation and galaxy evolution on cosmic scales. Cygnus X-1, as a nearby and well-studied example, provides valuable insights into these feedback mechanisms. The jets from Cygnus X-1 have been observed across multiple wavelengths, from radio to X-rays. By studying how the emission varies with wavelength and over time, astronomers can infer the properties of the particles in the jets, their velocities, and the magnetic fields that shape them. This multi-wavelength approach has been crucial in developing our understanding of relativistic jets from black holes. All these peculiarities and puzzles make Cygnus X-1 not just historically significant as the first confirmed black hole, but also scientifically valuable as a laboratory for studying extreme astrophysical processes. Each anomaly challenges our understanding and pushes us to refine our theories of stellar evolution, black hole formation, and accretion physics. But perhaps the most profound aspect of Cygnus X-1's strangeness is what it tells us about the limits of our knowledge. Despite decades of study and the application of our most sophisticated theories and instruments, this system continues to surprise us. It reminds us that the universe is not obligated to conform to our expectations or to fit neatly into our theoretical frameworks. In science, anomalies like Cygnus X-1 are particularly valuable. They highlight the boundaries of our understanding and point the way toward new discoveries. As physicist Richard Feynman once noted, "The thing that doesn't fit is the thing that's the most interesting." Cygnus X-1, with its many peculiarities, certainly qualifies as interesting by this standard. The continuing mysteries of this system also remind us of the iterative nature of scientific progress. Our understanding of Cygnus X-1 has evolved significantly since its discovery, with each new observation and theoretical insight refining our picture of this remarkable binary. This process is ongoing, with current and future observatories poised to reveal more about this enigmatic system. As technology advances, our ability to observe and analyze Cygnus X-1 continues to improve. Space-based X-ray observatories like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton provide detailed spectroscopic information about the accretion disk and the environment near the black hole. Radio telescopes like the Very Long Baseline Array allow us to study the jets with unprecedented resolution. And theoretical advances, including sophisticated computer simulations, help us interpret these observations within the framework of general relativity and plasma physics. Despite these advances, Cygnus X-1 retains its mysteries. Its mass, its spin, its formation history, its variability, all continue to pose challenges to our understanding. Each answered question seems to raise new ones in the endless cycle of scientific inquiry. As we lie here, contemplating the dance of the black hole and its stellar companion, let us appreciate the beautiful complexity of the cosmos. Let us marvel at the fact that, through human ingenuity and persistence, we can study objects thousands of light years away and discern their properties. And let us wonder at the mysteries that remain, the questions still unanswered about Cygnus X-1 and the countless other black holes scattered throughout our universe. In the next chapter, we will explore the intricate anatomy of this binary system in more detail, examining the relationship between the black hole and its companion star, the structure of the accretion disk, and the mechanisms that produce the powerful X-ray emissions and relativistic jets. But for now, let us simply appreciate the profound strangeness of Cygnus X-1, a cosmic enigma that continues to challenge and inspire astronomers and astrophysicists around the world. As sleep draws nearer, consider that the light from this system, the X-rays detected by our satellites and the visible light from the companion star, has traveled through space for thousands of years to reach us. It brings us information from a distant part of our galaxy, from a time when human civilization was in its infancy. Yet through the tools of modern science, we can decipher this ancient light and learn about one of the most extreme environments in the cosmos. Cygnus X-1, the black hole that should not exist, yet does, a cosmic paradox that reminds us of how much we have learned about our universe and how much we still have to discover. A silent sentinel in the constellation of the Swan, guarding secrets about the nature of space, time, and gravity that we are only beginning to unravel. Rest now, as we prepare to delve deeper into the mysteries of this remarkable system in the chapters to come. Let your mind drift toward that invisible giant in the sky, pulling matter from its stellar companion, warping space-time around it, challenging our understanding with its very existence. In the darkness of space, Cygnus X-1 awaits, a black hole with many stories still to tell, environment, which in turn can influence the future accretion onto the black hole. All these peculiarities and puzzles make Cygnus X-1 not just historically significant as the first confirmed black hole, but also scientifically valuable as a laboratory for studying extreme astrophysical processes. Each anomaly challenges our understanding and pushes us to refine our theories of stellar evolution, black hole formation, and accretion physics. But perhaps the most profound aspect of Cygnus X-1's strangeness is what it tells us about the limits of our knowledge. Despite decades of study and the application of our most sophisticated theories and instruments, this system continues to surprise us. It reminds us that the universe is not obligated to conform to our expectations or to fit neatly into our theoretical frameworks. In science, anomalies like Cygnus X-1 are particularly valuable. They highlight the boundaries of our understanding and point the way toward new discoveries. As physicist Richard Feynman once noted, "The thing that doesn't fit is the thing that's the most interesting." Cygnus X-1, with its many peculiarities, certainly qualifies as interesting by this standard. The continuing mysteries of this system also remind us of the iterative nature of scientific progress. Our understanding of Cygnus X-1 has evolved significantly since its discovery, with each new observation and theoretical insight refining our picture of this remarkable binary. This process is ongoing, with current and future observatories poised to reveal more about this enigmatic system. As we lie here, contemplating the dance of the black hole and its stellar companion, let us appreciate the beautiful complexity of the cosmos. Let us marvel at the fact that, through human ingenuity and persistence, we can study objects thousands of light years away and discern their properties. And let us wonder at the mysteries that remain, the questions still unanswered about Cygnus X-1 and the countless other black holes scattered throughout our universe. In the next chapter, we will explore the intricate anatomy of this binary system in more detail, examining the relationship between the black hole and its companion star, the structure of the accretion disk, and the mechanisms that produce the powerful X-ray emissions and relativistic jets. But for now, let us simply appreciate the profound strangeness of Cygnus X-1, a cosmic enigma that continues to challenge and inspire astronomers and astrophysicists around the world. As sleep draws nearer, consider that the light from this system, the X-rays detected by our satellites, and the visible light from the companion star, has traveled through space for thousands of years to reach us. It brings us information from a distant part of our galaxy, from a time when human civilization was in its infancy. Yet through the tools of modern science, we can decipher this ancient light and learn about one of the most extreme environments in the cosmos. Cygnus X-1, the black hole that should not exist, yet does. A cosmic paradox that reminds us of how much we have learned about our universe and how much we still have to discover. A silent sentinel in the constellation of the Swan, guarding secrets about the nature of space, time, and gravity that we are only beginning to unravel. Rest now, as we prepare to delve deeper into the mysteries of this remarkable system in the chapters to come. Let your mind drift toward that invisible giant in the sky, pulling matter from its stellar companion, warping space-time around it, challenging our understanding with its very existence. In the darkness of space, Cygnus X-1 awaits, a black hole with many stories still to tell. As we continue our exploration of Cygnus X-1, let us turn our attention to the intricate structure of this remarkable binary system. Like a cosmic clockwork of extraordinary complexity, Cygnus X-1 consists of multiple components working together in a delicate gravitational ballet. Understanding this anatomy helps us appreciate not only the beauty of this particular system, but also provides insights into similar binary black holes throughout our galaxy. At the heart of Cygnus X-1 are two massive objects: the black hole itself and its stellar companion, the blue supergiant star designated HDE 226868. Let us begin our examination with this visible partner, the only component of the system we can actually see with optical telescopes. HDE 226868 is a truly magnificent star. With approximately 40 times the mass of our Sun, it belongs to the most massive class of stars in our galaxy. Its surface temperature is about 30,000 degrees Celsius, more than 5 times hotter than our Sun. This extreme temperature gives it its characteristic blue color, as hotter stars emit more blue light than cooler ones, like our yellow Sun. The star is classified as a blue supergiant, indicating both its color and its enormous size. If placed at the center of our solar system, this star would extend far beyond the orbit of Mercury, possibly approaching Venus. Its tremendous size is a result of its advanced evolutionary state. Despite being only a few million years old, this star has already exhausted the hydrogen in its core and has begun to expand as it fuses heavier elements. Blue supergiants like HDE 226868 are relatively rare in our galaxy because they represent a short-lived phase in the life of massive stars. They evolve rapidly, burning through their nuclear fuel at a prodigious rate. The more massive a star, the faster it burns its fuel and the shorter its lifespan. While our Sun will live for about 10 billion years, HDE 226868 might only exist for a few million years before it too explodes as a supernova. This star is notable not only for its mass and temperature, but also for its powerful stellar wind. Unlike the relatively gentle solar wind produced by our Sun, the wind from HDE 226868 is a tempestuous outflow of particles, driven by the intense radiation pressure from its hot surface. This wind carries away material at rates thousands of times greater than our Sun's solar wind, with particles moving at speeds of several thousand kilometers per second. The stellar wind plays a crucial role in the Cygnus X-1 system. Some portion of this outflowing material does not escape the system entirely, but is captured by the gravitational pull of the black hole. This captured material forms the accretion disk, the source of the powerful X-ray emissions that led to the discovery of Cygnus X-1. The process of mass transfer in this system is complex and not fully understood. In some binary systems, matter flows directly from one star to another through what astronomers call the inner Lagrangian point, a region where the gravitational forces of the two objects balance precisely. This creates a stream of material flowing from donor to recipient. In Cygnus X-1, however, the process appears to be different. Rather than direct transfer through a Lagrangian point, the black hole captures a portion of the stellar wind from its companion. This is sometimes called wind accretion, as opposed to Roche-Lobe overflow. The distinction is important because it affects the rate of mass transfer and the long-term evolution of the system. As this captured material approaches the black hole, it cannot fall directly inward due to its angular momentum, the same physical principle that keeps planets in orbit around the Sun. Instead, the material forms a swirling disk around the black hole, with particles gradually spiraling inward as they lose energy through collisions with other particles. This accretion disk is one of the most fascinating components of the Cygnus X-1 system. Though we cannot observe it directly with optical telescopes, its presence is revealed through its powerful X-ray emissions. The disk spans a range of distances from the black hole, from thousands of kilometers at its outer edge to just a few kilometers at its inner boundary near the event horizon. The accretion disk is not uniform, but varies in density, temperature, and thickness at different distances from the black hole. The outer regions are relatively cool, with temperatures of perhaps tens of thousands of degrees Celsius. As material spirals inward, it is compressed and heated by gravitational energy being converted to thermal energy. By the time it reaches the inner regions of the disk, the temperature has soared to millions of degrees. At these extreme temperatures, the disk emits primarily in X-rays, with the inner regions producing the highest energy radiation. The spectrum of this radiation provides valuable information about the conditions in the disk and the properties of the black hole itself. By carefully analyzing this spectrum, astronomers can infer details about the black hole's mass, spin, and the rate at which it is accreting material. The inner edge of the accretion disk is determined by the black hole's properties, particularly its spin. For a non-rotating black hole, the innermost stable circular orbit, the closest an object can orbit without inevitably falling in, is at 3 times the Schwarzschild radius, the radius of the event horizon. But for a rapidly rotating black hole like Cygnus X-1, this innermost stable orbit moves much closer to the event horizon, allowing the accretion disk to extend nearer to the black hole. This proximity to the event horizon means that the material in the inner accretion disk is moving at a significant fraction of the speed of light. It also experiences extreme gravitational forces and is subject to various relativistic effects predicted by Einstein's theory of general relativity. Time dilation, the slowing of time in strong gravitational fields, affects the inner regions of the disk. Gravitational redshift causes radiation emitted from these regions to lose energy as it climbs out of the black hole's gravitational well. Beyond the accretion disk, but still part of the Cygnus X-1 system, are the relativistic jets. These are narrow beams of particles, primarily electrons and positrons, ejected from the regions near the black hole at velocities approaching the speed of light. These jets extend perpendicular to the plane of the accretion disk, channeling a portion of the energy released by the accreting material into two opposite directions. The mechanism that produces these jets is not fully understood, but it likely involves the interaction of the accretion disk with the black hole's magnetic field. As the disk rotates, it can drag and twist magnetic field lines, creating a configuration that accelerates charged particles along the rotational axis of the system. The rapid rotation of Cygnus X-1's black hole, which we discussed in the previous chapter, may play a crucial role in powering these jets. The jets from Cygnus X-1 are modest compared to those observed from some other systems, particularly the supermassive black holes at the centers of active galaxies. Nevertheless, they represent a significant channel through which energy escapes from the system. They also interact with the surrounding interstellar medium, creating shock waves and heating the gas around the binary system. Surrounding this entire complex is a diffuse cloud of ionized gas, heated by the X-ray emission from the accretion disk and the ultraviolet radiation from the blue supergiant star. This cloud, sometimes called a corona, extends much further than the binary system itself and represents the interface between Cygnus X-1 and the wider interstellar medium. The anatomy of Cygnus X-1 is not static but dynamic, changing on multiple timescales. On the shortest timescales, milliseconds to seconds, turbulence and instabilities in the inner accretion disk cause rapid fluctuations in the X-ray emission. On intermediate timescales, hours to days, the orbital motion of the binary affects the geometry of the system and the rate of mass transfer. And on longer timescales, weeks to years, the system can transition between different accretion states, with changes in the structure of the disk and the strength of the jets. These changes are most evident in the X-ray behavior of the system. Astronomers recognize several distinct states, primarily distinguished by the energy distribution of the X-ray emission and the presence or absence of jets. In the hard state, the X-ray spectrum peaks at higher energies, and powerful jets are present. In the soft state, lower energy, X-rays dominate, and the jets are suppressed or absent. There are also intermediate and transitional states as the system moves between these extremes. The transitions between these states are thought to be driven by changes in the rate of mass accretion onto the black hole. When the accretion rate is low, the disk is geometrically thick, but optically thin, meaning radiation can escape easily. This configuration produces the hard state, with high-energy X-rays and jets. When the accretion rate increases, the disk becomes thinner and optically thick, leading to the soft state dominated by lower-energy thermal emission. These state transitions in Cygnus X-1 and similar systems provide a valuable opportunity to study how accretion disks behave under different conditions. They help astronomers understand the complex interplay between gravity, radiation, and magnetic fields in some of the most extreme environments in the universe. Another fascinating component of the Cygnus X-1 anatomy, though one that is purely theoretical, is the region immediately surrounding the event horizon. Here, the extreme gravitational field of the black hole creates a phenomenon known as frame dragging, where spacetime itself is dragged around by the rotation of the black hole. This effect creates a region called the ergosphere, where nothing can remain stationary with respect to distant observers. The ergosphere extends slightly beyond the event horizon and is shaped like an oblate spheroid, flattened at the poles. Within this region, particles can still escape from the black hole's gravity, unlike those that cross the event horizon. But they are forced to rotate in the same direction as the black hole, a consequence of the dragging of spacetime. Theoretical physicists have speculated that the ergosphere might play a role in powering the jets observed from systems like Cygnus X-1. The Penrose process, named after mathematician Roger Penrose, who first proposed it, suggests that particles entering the ergosphere might split in two, with one portion falling into the black hole and the other escaping with more energy than the original particle. This could provide a mechanism for extracting energy from the black hole's rotation. Beyond the ergosphere lies the event horizon itself, the boundary beyond which nothing, not even light, can escape. For a rotating black hole like the one in Cygnus X-1, the event horizon is not spherical but oblate, bulging at the equator due to the centrifugal force of rotation. The radius of this horizon is smaller than it would be for a non-rotating black hole of the same mass, another effect of the rapid spin. What lies beyond the event horizon is a subject of intense theoretical interest, but is, by definition, unobservable. According to general relativity, within the event horizon, all paths lead inexorably toward the central singularity, a point of infinite density where the laws of physics as we currently understand them break down. Quantum theories of gravity, which attempt to reconcile general relativity with quantum mechanics, suggest that the singularity might be avoided, but such theories remain speculative and unverified. The entire Cygnus X-1 system, from the outer atmosphere of the blue supergiant to the event horizon of the black hole, represents a cosmic laboratory for studying physics under extreme conditions. Temperatures range from thousands to millions of degrees. Densities span from the near vacuum of space to the incredible density of matter near a black hole. Magnetic fields twist and reconnect. Particles accelerate to nearly the speed of light, and gravity warps the very fabric of space-time. Despite this complexity, the system as a whole exhibits remarkable stability. The binary has likely been in a configuration similar to its current state for thousands or millions of years, with the black hole steadily accreting material from its companion, while the blue supergiant gradually evolves toward its own eventual supernova. This stability will not last forever, however. As the companion star continues to evolve, it will eventually exhaust its nuclear fuel and begin to expand even further. This expansion will increase the rate of mass transfer to the black hole, potentially leading to a more dramatic interaction between the two objects. Eventually, the companion will reach the end of its life, possibly exploding as a supernova and leaving behind a neutron star or a second black hole. If a second black hole forms, and if the binary survives this transformation, Cygnus X-1 would become what astronomers call a binary black hole system. Such systems are of great interest for gravitational wave astronomy, as the two black holes would gradually spiral toward each other, emitting gravitational waves that might eventually be detected by observatories like LIGO or its successors. This potential future for Cygnus X-1 reminds us that what we observe is just a snapshot in the long cosmic evolution of this system. The black hole and its companion have a history stretching back to their formation from a molecular cloud, through their early evolution as massive stars, to the collapse of one into a black hole. And they have a future that will continue long after our observations cease, possibly culminating in a merger of two black holes millions or billions of years from now. Our understanding of the anatomy of Cygnus X-1 has been pieced together through decades of observation across multiple wavelengths, from radio to X-rays. Each new generation of telescopes and instruments has revealed more details and refined our picture of this remarkable system. Yet much remains to be learned, particularly about the processes occurring closest to the black hole, where our observational capabilities are most limited. Future observatories may provide even more detailed views of systems like Cygnus X-1. X-ray telescopes with higher resolution and sensitivity will better resolve the structure of the accretion disk. Radio interferometers with longer baselines will provide sharper images of the jets. And gravitational wave detectors may eventually be sensitive enough to detect the subtle warping of space-time caused by the orbital motion of a black hole and its stellar companion. For now, we can marvel at the intricate cosmic machine that is Cygnus X-1, a blue supergiant star, 40 times the mass of our Sun, orbiting with a black hole 21 times the Sun's mass. An accretion disk of superheated gas spiraling toward the event horizon, jets of particles shooting out at nearly the speed of light, all choreographed by the inexorable force of gravity, following the curved paths in space-time described by Einstein's equations. As we drift towards sleep, imagine this cosmic dance occurring thousands of light years away in the constellation of the Swan, invisible to our eyes but revealed through the ingenuity of human science. A reminder of the extraordinary phenomena that exist in our universe and of our remarkable ability to understand them, despite their distance and their extreme nature. In the next chapter, we will explore the evidence that convinces astronomers that Cygnus X-1 truly contains a black hole. What observations and measurements lead to this conclusion, and how certain can we be of this interpretation? But for now, let the mental image of this binary system, with its massive star feeding material to its dark companion, accompany you toward restful contemplation of the wonders of our cosmos. In our journey exploring Cygnus X-1, we have spoken with confidence about the black hole at the heart of this system. Yet a fundamental question remains: how do we know it's actually a black hole? After all, black holes are, by definition, invisible. Their gravitational pull is so strong that not even light can escape from within their event horizons. So, how can astronomers be so certain that what lurks in Cygnus X-1 is truly a black hole and not some other exotic cosmic object? This question touches on a fundamental aspect of science. In astronomy, perhaps more than in any other field, direct observation is often impossible. We cannot travel to distant stars or galaxies to examine them up close. We certainly cannot venture near a suspected black hole to confirm its nature. Instead, astronomers must rely on indirect evidence, on the observable effects these objects have on their surroundings, and on the predictions of well-established theories. The case for Cygnus X-1 containing a black hole is built on multiple lines of evidence, each adding to the confidence of this conclusion. Let us explore these evidences one by one, understanding how astronomers have come to accept the black hole interpretation of this remarkable system. The first and perhaps most compelling piece of evidence is the mass of the invisible companion to HDE 226868. As we have discussed in previous chapters, careful analysis of the orbital motion of the visible star allows astronomers to calculate the mass of its unseen partner. Modern measurements place this mass at approximately 21 times that of our Sun. This mass determination relies on Kepler's laws of planetary motion, formulated in the early 17th century but still fundamental to astronomy today. By measuring the period of the orbit, the separation between the two objects, and the velocity of the visible star as it moves in its orbit, astronomers can calculate the mass of both components of the system. The specific technique used is spectroscopic analysis. Astronomers observe the spectrum of the visible star, breaking its light into its component wavelengths. As the star moves in its orbit, sometimes toward us and sometimes away, its spectral lines shift slightly due to the Doppler effect, the same phenomenon that causes the pitch of a siren to change as an ambulance passes by. By carefully measuring these shifts over the course of the orbital period, astronomers can determine the star's velocity at different points in its orbit. This velocity pattern reveals not only the mass of the invisible companion, but also the inclination of the orbit relative to our line of sight. If we were viewing the orbit edge-on, the star would move directly toward and away from us, maximizing the observed Doppler shifts. If we were viewing the orbit face-on, we would see no Doppler shifts at all. By analyzing the observed pattern, astronomers can determine both the true orbital velocity and the inclination angle. The calculation is complicated by several factors. The orbit is not perfectly circular but slightly elliptical. The plane of the orbit is tilted relative to our line of sight, so we see the motion projected on the sky rather than directly. And the companion star is not a point source, but an extended object with complex internal motions. Nevertheless, with careful observation and analysis, astronomers have refined their mass estimates over the decades. The significance of this 21 solar mass measurement lies in what we know about other celestial objects. White dwarfs, the dense remnants of stars like our Sun, cannot exceed about 1.4 solar masses without collapsing under their own gravity. This limit, known as the Chandrasekhar limit, after the Indian-American astrophysicist who first calculated it, is a fundamental constraint based on the quantum mechanical properties of electron-degenerate matter. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers as a planetary nebula and leaves behind its core as a white dwarf. This core, no longer supported by the outward pressure of nuclear fusion, would collapse under its own gravity were it not for a quantum mechanical effect called electron degeneracy pressure. According to the Pauli exclusion principle, no two electrons can occupy the same quantum state. This creates a resistance to further compression that can support the star against gravity, but only up to the Chandrasekhar limit. If a white dwarf somehow gains enough mass to exceed this limit, perhaps by accreting material from a companion star in a binary system, it will collapse catastrophically. This collapse typically triggers a Type Ia supernova, completely destroying the white dwarf. But even without such a dramatic end, the fundamental physics of electron degeneracy pressure ensures that no stable white dwarf can exist above the Chandrasekhar limit. Neutron stars, Even denser stellar remnants formed in the deaths of more massive stars also have a maximum mass. While the exact value is still a subject of research and depends on the equation of state of nuclear matter, most estimates place it between 2 and 3 solar masses. Beyond this threshold, the pressure from neutron degeneracy cannot counteract gravity, and the object must collapse further. Neutron stars form when the core of a massive star collapses during a supernova explosion. If the core is massive enough to overcome electron degeneracy pressure but not so massive as to collapse completely to a black hole, it will compress until the electrons and protons in its constituent atoms combine to form neutrons. Like electron degeneracy pressure in white dwarfs, neutron degeneracy pressure can support the star against further collapse, but only up to a limit. This limit is less precisely known than the Chandrasekhar limit for white dwarfs because the behavior of matter at the extreme densities found in neutron stars is not fully understood. Different theoretical models of the equation of state of nuclear matter predict slightly different maximum masses, but all credible models place this limit well below 21 solar masses, typically around 2 to 3 solar masses. The invisible companion in Cygnus X-1, with its 21 solar masses, far exceeds these limits. It simply cannot be a white dwarf or a neutron star, according to our current understanding of physics. What about a cluster of smaller objects, perhaps multiple neutron stars, orbiting each other closely enough to appear as a single object from our perspective? This alternative explanation faces several problems. Such a cluster would be dynamically unstable over astronomical timescales. The individual objects would interact gravitationally, eventually ejecting some members and causing others to collide or merge. Moreover, the X-ray emission pattern observed from Cygnus X-1 is consistent with a single compact object surrounded by an accretion disk, not with multiple smaller sources. For a cluster of neutron stars to mimic the gravitational effects of a single 21 solar mass object, they would need to be confined within a very small volume, probably no more than a few hundred kilometers across. At such close proximity, these neutron stars would inevitably spiral toward each other due to the emission of gravitational waves, merging on timescales much shorter than the estimated age of the Cygnus X-1 system. Furthermore, if Cygnus X-1 contained multiple neutron stars rather than a single black hole, we would expect to observe certain distinctive signatures. Neutron stars typically have strong magnetic fields that channel accreting material onto their magnetic poles, creating hotspots that produce pulsed X-ray emission as the star rotates. The absence of such pulsations in Cygnus X-1 argues against a neutron star interpretation. Could it be an unusual type of star, perhaps one that emits little visible light? This too seems implausible. Any star massive enough to account for the gravitational effects observed would necessarily be very hot and luminous due to the nuclear reactions in its core. It would be easily detectable in infrared or other wavelengths, yet observations across the electromagnetic spectrum reveal no such object. Stars generate energy through nuclear fusion in their cores, and this energy production is directly related to their mass. A star with 21 solar masses would produce energy at an enormous rate, making it one of the most luminous objects in our galaxy. Even if some exotic mechanism prevented this energy from escaping as visible light, it would have to emerge in some form, whether as infrared radiation, neutrinos, or other particles. Sensitive observations across the electromagnetic spectrum have detected no such emissions from the location of the invisible companion. Having eliminated these alternatives, astronomers are left with the black hole hypothesis. A black hole with 21 solar masses would exert exactly the gravitational influence observed in Cygnus X-1 while remaining completely invisible itself. According to Einstein's theory of general relativity, nothing prevents the formation of such an object from the collapse of a sufficiently massive star. The mass evidence alone makes a compelling case for a black hole in Cygnus X-1, but astronomers have gathered additional evidence that strengthens this conclusion even further. The second line of evidence comes from the X-ray emissions of the system, which reveal information about the environment very close to the invisible companion. X-ray telescopes like NASA's Chandra and the European Space Agency's XMM Newton have observed Cygnus X-1 in great detail. The spectrum of X-rays, the distribution of radiation across different energies, provides clues about the temperature, density, and motion of the emitting material. The X-ray spectrum of Cygnus X-1 is consistent with an accretion disk of superheated gas spiraling into a black hole. This spectrum shows several distinctive features. There is a thermal component, radiation with a distribution of energies characteristic of hot gas, with temperatures of millions of degrees. This comes primarily from the accretion disk. There is also a non-thermal component, particularly evident when the system is in its hard state, which is thought to arise from a corona of even hotter gas surrounding the inner disk or from the base of the jets. The thermal component provides information about the temperature and structure of the accretion disk. The inner edge of this disk, where it approaches the black hole, is hotter than the outer regions. The temperature gradient and the overall shape of the spectrum are consistent with theoretical models of accretion disks around black holes, where gravitational energy is converted to heat as matter spirals inward. Particularly telling are the rapid variations in the X-ray output. Cygnus X-1 can change its brightness significantly on timescales as short as milliseconds. Such rapid variability indicates that the emission region must be very small. Light travel time arguments suggest that a source cannot vary significantly faster than the time it takes light to cross it. For millisecond variability, this implies an emission region no larger than a few hundred kilometers across, consistent with the inner regions of an accretion disk around a stellar mass black hole. These rapid fluctuations, known as quasi-periodic oscillations or QPOs, have frequencies that relate to orbital motions very close to the black hole. Some oscillations correspond to material orbiting just outside the innermost stable circular orbit, the closest that matter can stably orbit, before inevitably falling toward the event horizon. The frequencies of these oscillations match theoretical predictions for matter orbiting a black hole of the inferred mass. QPOs are observed in several types of accreting systems, including neutron star binaries. However, the specific pattern of frequencies observed in Cygnus X-1 and the way these frequencies evolve during state transitions are characteristic of black hole systems. This provides another piece of evidence distinguishing Cygnus X-1 from neutron star alternatives. The X-ray spectrum also reveals the presence of an extremely broad ion emission line. This line, produced when ion atoms in the accretion disk are struck by high-energy X-rays, appears smeared out due to the combined effects of Doppler shifting from the rapidly orbiting material and gravitational redshifting from the strong gravitational field near the black hole. The shape of this line provides information about the spin of the black hole and confirms that the emitting material is orbiting very close to the event horizon. Ion emission lines are particularly useful for this analysis because iron is abundant in the accretion disk and produces a strong, distinctive spectral feature. In the absence of relativistic effects, this line would appear narrow and well-defined. The extreme broadening observed in Cygnus X-1 requires that the emitting material is orbiting at a significant fraction of the speed of light in a region where space-time is strongly curved by the black hole's gravity. Detailed modeling of this ion line, taking into account all the relativistic effects, provides an independent constraint on the mass and spin of the black hole. The results are consistent with the mass derived from the orbital motion of the companion star and indicate a rapidly spinning black hole, with a spin parameter close to the maximum value allowed by general relativity. Another piece of evidence comes from the observation of relativistic jets emanating from Cygnus X-1. These narrow beams of particles, accelerated to velocities approaching the speed of light, are a common feature of accreting black hole systems. They form through complex interactions between the infalling matter, magnetic fields, and the black hole's gravity. The presence of such jets in Cygnus X-1 is consistent with a black hole interpretation and provides additional constraints on the system's properties. Radio observations have mapped these jets with high precision, revealing their structure and behavior. The jets are highly collimated, maintaining their narrow shape over significant distances. This collimation is believed to result from the interaction of the outflowing material with the strong magnetic fields near the black hole. The jets also show evidence of precession, a slow change in their orientation that may be related to the spin of the black hole or interactions with the accretion disk. The jets from Cygnus X-1, like those from other black hole systems, display a characteristic relationship between their radio and X-ray emissions. This correlation, known as the fundamental plane of black hole activity, relates the radio luminosity, X-ray luminosity, and mass of the black hole. Cygnus X X-1 falls precisely where expected on this plane for a black hole of its mass, providing further support for the black hole interpretation. While neutron stars can also produce jets, the specific properties of the jets from Cygnus X-1, including their power, collimation, and variability, are more consistent with a black hole origin. This represents another strand in the web of evidence pointing toward the black hole nature of this system. The behavior of Cygnus X-1 during state transitions provides yet more evidence for its black hole nature. As discussed in previous chapters, the system can transition between different emission states, particularly the soft state dominated by thermal emission from the accretion disk, and the hard state characterized by higher energy X-rays and strong jets. These transitions, observed in many black hole binaries, involve complex changes in the accretion flow and the environment near the event horizon. The pattern of these state transitions, the correlations between different types of emission, and the timescales involved all match theoretical models of accretion onto black holes. While neutron stars also show state transitions, the specific behaviors observed in Cygnus X-1 and similar systems distinguish them from neutron star binaries and support the black hole interpretation. During these transitions, the system follows a characteristic path in what astronomers call the hardness intensity diagram, a plot of the total X-ray brightness against the ratio of high energy to low energy X-rays. The path forms a loop, with the system evolving in a predictable way as it moves between states. This pattern is now recognized as a signature of black hole binaries and provides another piece of evidence for the nature of Cygnus X-1. Perhaps the most sophisticated evidence comes from detailed modeling of the accretion process using general relativistic magnetohydrodynamic simulations. These computer models solve Einstein's equations of general relativity coupled with the equations of magnetohydrodynamics, which describe how electrically conducting fluids like the ionized gas in the accretion disk behave in magnetic fields. By simulating the accretion process under different conditions and comparing the results to observations, astronomers can test whether the black hole hypothesis is consistent with the data. These simulations predict specific patterns of emission, variability, and spectral features that match what is observed in Cygnus X-1. They can reproduce the broad iron line, the quasi-periodic oscillations, and the transitions between different states. The agreement between these sophisticated models and the observations provides strong support for the black hole interpretation. It's worth noting that the evidence for a black hole in Cygnus X-1 has grown stronger over time. When the system was first discovered in the 1960s, the black hole hypothesis was just one possibility among several. As observations improved and theoretical understanding advanced, alternative explanations were gradually ruled out, and the case for a black hole became increasingly compelling. The progress in X-ray astronomy has been particularly important. Early observations could only detect the presence of X-ray emission from the general direction of Cygnus X-1. Modern X-ray telescopes can resolve detailed spectral features, track rapid variability, and even create images of the X-ray emitting regions. Each advance in observational capability has provided new tests of the black hole hypothesis, and it has passed them all. Similarly, theoretical advances have strengthened the case. Early models of accretion onto black holes were relatively simple, capturing only the basic gravitational effects. Modern simulations include general relativity, magnetohydrodynamics, radiation transport, and other complex physical processes. These more sophisticated models make specific predictions that can be tested against observations, and the agreement between theory and observation continues to improve. Despite this overwhelming evidence, it's important to acknowledge that science never provides absolute proof. All scientific conclusions are provisional, subject to revision if new evidence emerges or if a better explanation is found. In the case of Cygnus X-1, while no one has directly seen the black hole, the indirect evidence from multiple independent lines of investigation all point to the same conclusion. The invisible companion to HDE 226868 is indeed a black hole. This approach, building a case on multiple lines of evidence rather than a single definitive observation, is common in astronomy and other sciences where direct access to the object of study is impossible. It's similar to how detectives might solve a crime without witnessing it directly, by piecing together forensic evidence, witness testimonies, and logical deductions. In recent years, new techniques have provided even more direct evidence for the existence of black holes in general, further strengthening the case for Cygnus X-1. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the dark region where light is captured by the event horizon against the background of glowing gas. This remarkable achievement, the culmination of decades of technological development and theoretical work, provided visual confirmation of the basic features predicted by general relativity. The subject of that historic image was not Cygnus X-1, but the supermassive black hole at the center of galaxy M87, a much larger and more distant object. Cygnus X-1 is too small and too surrounded by obscuring material for current technology to image its event horizon directly. Nevertheless, the M87 image confirmed the reality of black holes and the accuracy of general relativistic predictions about their nature, adding confidence to the identification of Cygnus X-1 as a stellar mass black hole. Similarly, the detection of gravitational waves from merging black holes by LIGO and Virgo, first announced in 2016, provided another independent confirmation of the existence of black holes. These ripples in space-time, produced when two black holes spiral together and merge, carry the distinctive signature predicted by general relativity. Dozens of such events have now been detected, establishing beyond reasonable doubt that black holes exist and behave as Einstein's theory predicts. While Cygnus X-1 itself has not produced detectable gravitational waves, as it is not currently merging with another black hole, these observations of other systems confirm the fundamental theory that predicts the existence of objects like the black hole in Cygnus X-1. They represent another strand in the web of evidence supporting the black hole interpretation. As our observational capabilities continue to advance, we may obtain even more direct evidence about the nature of Cygnus X-1. Future X-ray telescopes with higher resolution and sensitivity will provide more detailed views of the environment near the black hole. Advanced radio interferometers might resolve the structure of the jets on smaller scales. And future gravitational wave detectors might be sensitive enough to detect the subtle ripples in space-time produced by the orbital motion of the black hole and its stellar companion. For now, the case for a black hole in Cygnus X-1 rests on the convergence of multiple lines of evidence: the high mass exceeding the limits for neutron stars, the characteristic X-ray emission from an accretion disk, the presence of relativistic jets, the rapid variability, indicating a small emission region, the spectral features showing relativistic effects, and the overall behavior matching theoretical predictions for black hole systems. Together, these create a compelling case that has convinced the vast majority of astronomers. This scientific journey, from the initial discovery of a mysterious X-ray source to the detailed characterization of a black hole binary system, exemplifies the power of the scientific method. By making observations, developing hypotheses, testing predictions, and gradually refining our understanding, we have come to recognize Cygnus X-1 as one of the most extraordinary objects in our galaxy, a place where matter disappears from our universe, where space-time is warped to its limits, and where the most extreme predictions of general relativity are realized. As we contemplate this remarkable scientific achievement, let us remember that we have accomplished it without ever leaving Earth. Through the careful analysis of light that has traveled thousands of years across space, through the application of physical laws discovered through centuries of scientific inquiry, and through the collaborative efforts of generations of astronomers, we have uncovered the nature of an object so extreme that it once seemed to belong only to the realm of theoretical physics or science fiction. Cygnus X-1, once a mysterious source of X-rays, is now recognized as a testament to the predictive power of Einstein's general theory of relativity and to the ingenuity of observers who have pieced together its true nature from subtle clues encoded in its radiation. As we drift towards sleep, let us appreciate this triumph of human curiosity, perseverance, and analytical thinking, which has revealed one of the most exotic objects in our cosmic neighborhood. And let us remember that while we speak with confidence about the black hole in Cygnus X-1, our understanding continues to evolve. New observations, more sophisticated models, and unexpected discoveries may yet reveal aspects of this system that we have not anticipated. Science is a journey without end, a continuous process of refinement and occasional revolution. The story of Cygnus X-1 is not yet complete, and future chapters may hold surprises that we cannot currently imagine. For now, we can say with considerable confidence that Cygnus X-1 contains a black hole, an object 21 times the mass of our Sun, compressed into a region from which nothing, not even light, can escape. An object that warps space-time around it, according to Einstein's equations. An object that accretes matter from its companion star, heating it to millions of degrees, and producing the X-rays that led to its discovery. An object that reminds us of the extraordinary phenomena that exist in our universe, and of our remarkable ability to understand them, despite their distance and their extreme nature. Journey, from the initial discovery of a mysterious X-ray source to the detailed characterization of a black hole binary system, exemplifies the power of the scientific method. By making observations, developing hypotheses, testing predictions, and gradually refining our understanding, we have come to recognize Cygnus X-1 as one of the most extraordinary objects in our galaxy, a place where matter disappears from our universe, where space-time is warped to its limits, and where the most extreme predictions of general relativity are realized. As we contemplate this remarkable scientific achievement, let us remember that we have accomplished it without ever leaving Earth. Through the careful analysis of light that has traveled thousands of years across space, through the application of physical laws discovered through centuries of scientific inquiry, and through the collaborative efforts of generations of astronomers, we have uncovered the nature of an object so extreme that it once seemed to belong only to the realm of theoretical physics or science fiction. Cygnus X-1, once a mysterious source of X-rays, is now recognized as a testament to the predictive power of Einstein's general theory of relativity and to the ingenuity of observers who have pieced together its true nature from subtle clues encoded in its radiation. As we drift towards sleep, let us appreciate this triumph of human curiosity, perseverance, and analytical thinking, which has revealed one of the most exotic objects in our cosmic neighborhood. And let us remember that while we speak with confidence about the black hole in Cygnus X-1, our understanding continues to evolve. New observations, more sophisticated models, and unexpected discoveries may yet reveal aspects of this system that we have not anticipated. Science is a journey without end, a continuous process of refinement and occasional revolution. The story of Cygnus X-1 is not yet complete, and future chapters may hold surprises that we cannot currently imagine. For now, we can say with considerable confidence that Cygnus X-1 contains a black hole, an object 21 times the mass of our Sun, compressed into a region from which nothing, not even light, can escape. An object that warps space-time around it, according to Einstein's equations. An object that accretes matter from its companion star, heating it to millions of degrees, and producing the X-rays that led to its discovery. An object that reminds us of the extraordinary phenomena that exist in our universe, and of our remarkable ability to understand them, despite their distance and their extreme nature. Having established that Cygnus X-1 does indeed harbor a black hole, we now turn to one of the most intriguing aspects of this remarkable system. Despite our confidence in its existence, according to many theoretical models of stellar evolution and black hole formation, Cygnus X-1 should not exist, at least not in its current form. And yet, against these theoretical expectations, it does. This paradox lies at the heart of why Cygnus X-1 continues to be such an important object of study more than 50 years after its discovery. To understand this contradiction, we need to explore how black holes like the one in Cygnus X-1 are thought to form, and why the particular characteristics of this system challenge our current understanding. The journey takes us through the life cycles of massive stars, the physics of stellar winds, the violent explosions of supernovae, and the complex interactions that occur in binary star systems. Let us begin with what we know about the black hole in Cygnus X-1. As discussed in previous chapters, it has a mass of approximately 21 times that of our Sun. It is orbiting a massive blue supergiant star, completing one orbit every 5.6 days. The black hole is spinning very rapidly, with a spin parameter greater than 0.95, where 1 represents the theoretical maximum. And the system as a whole appears to have a relatively high space velocity compared to neighboring stars, suggesting that it received a kick at some point in its history. According to the standard model of stellar evolution, black holes form from the collapsed cores of massive stars. When a star with more than about 20 solar masses exhausts its nuclear fuel, its core collapses, while its outer layers are expelled in a supernova explosion. If the core is massive enough, typically more than about 3 solar masses, no known force can stop the collapse, and a black hole forms. This basic picture seems straightforward enough. A very massive star reaches the end of its life, explodes as a supernova, and leaves behind a black hole. But when we look at the details, especially in the context of Cygnus X-1, complications arise that challenge this simple narrative. The first major puzzle concerns the mass of the black hole. At 21 solar masses, it is significantly more massive than most stellar mass black holes in our galaxy. While this might not seem surprising given that it formed from a massive star, it creates a theoretical challenge because of a phenomenon known as stellar wind mass loss. Throughout their lives, massive stars lose material through stellar winds, streams of particles driven from their surfaces by the pressure of their intense radiation. This mass loss is particularly strong in stars with high metallicity, meaning those that contain a significant fraction of elements heavier than helium. These heavier elements, such as carbon, oxygen, and iron, provide more opportunities for the star's radiation to interact with matter, driving stronger winds. Stars in the disk of our galaxy, including the progenitor of Cygnus X-1's black hole, typically have relatively high metallicity because they formed from material enriched by previous generations of stars. According to theoretical models, a massive star in our galaxy should lose a substantial fraction of its mass through these winds before reaching the end of its life. This mass loss should be so significant that even if the star began with 50 or 60 solar masses, it might end up with only 15 to 20 solar masses by the time it explodes as a supernova. Furthermore, the supernova explosion itself should eject additional mass, leaving behind a black hole with perhaps 10 to 15 solar masses at most. Yet the black hole in Cygnus X-1 has 21 solar masses, significantly higher than these predictions. It seems to have retained more of its progenitor's mass than our models suggest it should have. This discrepancy indicates that either our understanding of stellar wind mass loss is incomplete, or the black hole in Cygnus X-1 formed through some unusual process. Perhaps the progenitor star had lower metallicity than typical for our region of the galaxy, resulting in weaker stellar winds and less mass loss. Or perhaps it gained mass from its companion through a process of mass transfer before collapsing to form a black hole. Another possibility is that the black hole formed through the merger of 2 smaller black holes or neutron stars. However, such a merger would produce strong gravitational waves and, in the case of neutron stars, a powerful electromagnetic counterpart, similar to the kilonova observed in 2017. No such event has been associated with Cygnus X-1, and the binary nature of the system, with its massive companion star, makes this scenario less likely. The mass puzzle becomes even more intriguing when we consider that the companion star, HDE 226868, is itself very massive, with approximately 40 solar masses. This suggests that the entire system began with an extraordinary amount of mass, perhaps with 2 stars of 50 to 60 solar masses each. Such massive binaries are rare, and their evolution is complex and not fully understood. The second major challenge to our understanding of Cygnus X-1 concerns its orbital characteristics. The black hole and its companion star orbit each other in a relatively tight, nearly circular orbit. This is puzzling because the formation of a black hole typically involves a supernova explosion, which should disrupt the binary system or, at minimum, leave it in a highly eccentric orbit. When a star explodes as a supernova, it can eject several solar masses of material in a matter of seconds. This sudden mass loss changes the gravitational dynamics of the binary system. If more than half the total mass of the binary is lost, the system becomes unbound, and the 2 components fly apart. Even if less mass is lost, the orbit typically becomes more eccentric, with the 2 objects sometimes approaching closely and at other times moving far apart. Yet Cygnus X-1 has a nearly circular orbit, with an eccentricity less than 0.1. This suggests that either the black hole formed without a powerful supernova explosion, or the binary somehow survived such an explosion with its orbit largely intact. Both scenarios are challenging for our current understanding. One possibility is that the black hole formed through a process called direct collapse, where the core of the massive star collapses directly to a black hole without a significant supernova explosion. This scenario might occur if the star is so massive that the collapsing core creates a black hole before the shock wave that would normally cause a supernova can develop. The material that would have been ejected in a supernova is instead captured by the black hole's gravity, resulting in minimal mass loss and little disruption to the binary orbit. Another possibility is that the progenitor star lost its outer layers more gradually, perhaps through interaction with its companion, before the core collapsed to form a black hole. This would be a less violent process than a typical supernova, and might allow the binary system to remain intact with a nearly circular orbit. A third scenario invokes a fallback supernova, where the star does explode, but much of the ejected material lacks sufficient velocity to escape the system and eventually falls back onto the newly formed black hole. This could result in a less dramatic change to the orbital dynamics, while still allowing for some mass ejection. Each of these scenarios faces its own challenges. Direct collapse should only occur in the most massive stars, typically those with initial masses above about 40 or 50 solar masses. Yet such stars should also experience strong stellar winds, bringing us back to the mass loss puzzle. A gradual loss of the outer layers through binary interaction might avoid a dramatic supernova, but it would need to occur in just the right way to maintain the observed orbital properties. And a fallback supernova would still be expected to significantly disturb the orbit, making the observed near-circular orbit difficult to explain. The third enigma of Cygnus X-1 is its rapid spin. As mentioned earlier, the black hole is rotating at nearly the maximum rate allowed by general relativity. This rapid rotation is challenging to explain, given our understanding of black hole formation. If the black hole formed from the collapse of a stellar core, its spin would depend on the rotation of that core just before collapse. Stars naturally rotate, but as they evolve, especially massive stars, they typically lose angular momentum through their stellar winds and through internal processes that transport angular momentum from the core to the outer layers. By the time a massive star reaches the end of its life, its core is usually rotating relatively slowly. For the black hole in Cygnus X-1 to be spinning so rapidly, either the progenitor star's core maintained a very rapid rotation despite these processes, or the black hole gained angular momentum after its formation. The latter could occur through the accretion of matter from the companion star, but calculations suggest that the amount of matter accreted over the lifetime of Cygnus X-1 is insufficient to spin up the black hole to the observed rate. The progenitor star might have kept its core rotating rapidly if it was in a close binary system from early in its life, with tidal interactions between the two stars affecting the internal rotation. But this would require a specific evolutionary path, and it's not clear whether such a mechanism could maintain sufficient core rotation to explain the observed spin. Another possibility is that the black hole formed with a more moderate spin but has been gradually spun up by accreting matter from its companion over millions of years. This scenario faces challenges as well, as the rate of accretion needed to achieve the observed spin is higher than what we estimate for Cygnus X-1 based on its X-ray luminosity. However, there might have been periods of more rapid accretion in the past that are not reflected in current observations. The fourth puzzle of Cygnus X-1 concerns the space velocity of the system. Recent measurements have shown that it is moving through the galaxy at a relatively high velocity compared to neighboring stars, about 100 kilometers per second relative to its surroundings. This suggests that the system received a kick at some point in its history. The most natural explanation for such a kick would be a supernova explosion. When a star explodes asymmetrically, with more material ejected in one direction than others, the remnant receives a recoil in the opposite direction, like a cosmic rocket. Many neutron stars show evidence of such kicks, with some moving through space at hundreds of kilometers per second. But here we encounter a contradiction. If the black hole in Cygnus X-1 formed through a significant supernova explosion, powerful enough to give the system its observed velocity, how did the binary survive with its nearly circular orbit intact? A strong enough explosion to provide the observed kick should also have significantly disrupted the orbit, yet this doesn't seem to have happened. One possibility is that the supernova was asymmetric in just the right way, imparting a velocity to the system as a whole, while minimally disturbing the relative orbits of the two components. This would require a remarkable coincidence, but given the vast number of binary systems in our galaxy, perhaps Cygnus X-1 represents a rare case where conditions were just right for this to occur. Another possibility is that the system gained its velocity not from a supernova but from gravitational interactions with other stars or with the spiral density waves of our galaxy. Over millions of years, such interactions could gradually increase the system's velocity relative to its surroundings. However, calculations suggest that these mechanisms are typically too weak to account for the observed velocity. A fifth puzzle concerns the evolutionary state of the companion star. HDE 226868 is a massive blue supergiant, a star in an advanced stage of evolution. Based on its properties, it is only a few million years old, which is extremely young by stellar standards. Yet it appears to be in a more advanced evolutionary state than we might expect given its age. For a binary system like Cygnus X-1 to have formed, the progenitor of the black hole must have completed its entire life cycle, from formation to supernova, within this short time frame. This is possible for very massive stars, which evolve rapidly, but it requires that the progenitor was significantly more massive than its companion, perhaps 60 or 70 solar masses, to the companion's 40. Yet, if the progenitor was so much more massive, we might expect it to have strongly influenced the evolution of its companion through tidal interactions and mass transfer. The companion might have gained mass from the progenitor before it collapsed, potentially explaining its current advanced evolutionary state despite its young age. But this complex exchange of material between the two stars makes the formation of such a massive black hole even more puzzling, as we might expect much of the progenitor's mass to have been transferred to the companion rather than being available to form the black hole. All these puzzles surrounding Cygnus X-1 point to a central challenge: our understanding of how massive stars evolve, how they interact in binary systems, and how they end their lives to form black holes is incomplete. Cygnus X-1, as the first confirmed black hole and one of the best studied, provides a crucial test case for our theories. Its very existence, with its particular set of characteristics, suggests that nature has found pathways to form black holes that we have not fully incorporated into our models. This is not unusual in the history of astronomy or science in general. Often, a well-studied object that defies our expectations becomes the key to advancing our understanding. Think of Mercury's orbital precession, which could not be fully explained by Newtonian physics and became one of the early confirmations of Einstein's theory of general relativity. Or consider pulsars, whose regular radio pulses initially baffled astronomers, but eventually led to our understanding of neutron stars. Cygnus X-1 may play a similar role in advancing our understanding of stellar evolution and black hole formation. Several lines of research are currently exploring the puzzles it presents. One area focuses on the role of metallicity in stellar wind mass loss. Recent studies suggest that the relationship between metallicity and mass loss may be more complex than previously thought, with other factors such as magnetic fields and rotation also playing important roles. If massive stars can retain more of their mass than our models have assumed, it might help explain the high mass of Cygnus X-1's black hole. Another research direction explores alternative pathways for black hole formation beyond the traditional supernova scenario. Direct collapse, fallback supernovae, and various forms of failed supernovae are being studied both observationally and theoretically. If some massive stars can collapse to form black holes without powerful explosions, it could explain both the high mass and the orbital characteristics of Cygnus X-1. The role of binary interactions in stellar evolution is also receiving increased attention. We now recognize that many massive stars exist in binary or multiple systems, and these interactions can significantly alter their evolutionary paths. Mass transfer, common envelope phases, and tidal interactions can all affect how stars evolve and end their lives. These processes may be key to understanding systems like Cygnus X-1. Perhaps most intriguingly, some researchers have suggested that Cygnus X-1 might be a window into an earlier epoch of stellar evolution in our galaxy. The progenitor of its black hole might have formed when the metallicity of the interstellar medium was lower than it is today, allowing it to retain more of its mass despite strong stellar winds. If this is the case, Cygnus X-1 might represent a transitional case between the very massive black holes that formed from the first generations of stars in the universe and the lower mass black holes forming in our galaxy today. This hypothesis is supported by the observation that the most massive stellar black holes, those with masses above about 25 solar masses, have mainly been detected through gravitational waves rather than through X-ray emission from binary systems. This suggests that such massive black holes might preferentially form in environments different from the current disk of our galaxy, perhaps in regions with lower metallicity or in the distant past when the galaxy's chemical composition was different. Cygnus X-1, with its 21 solar mass black hole, might represent an intermediate case, formed under conditions that were more conducive to producing massive black holes than the typical environment in our galaxy today, but still within the range of possibilities for black hole formation in binary systems. The existence of Cygnus X-1, despite theoretical expectations that it should not exist in its current form, reminds us of the limitations of our understanding and the complexity of the universe. It serves as a humbling reminder that nature often finds ways to create structures and systems that our theories have not fully anticipated or explained. This is not a failure of science, but rather an opportunity for growth and refinement. The discrepancies between our theoretical expectations and the observed reality of Cygnus X-1 drive research forward, leading to more sophisticated models and a deeper understanding of the processes involved in stellar evolution and black hole formation. In this sense, Cygnus X-1 plays a dual role in the history of astronomy. On one hand, it represents a triumph of observational and theoretical work, confirming the existence of black holes and providing a laboratory for studying extreme physics. On the other hand, it presents ongoing challenges to our understanding, reminding us that the universe is more complex and varied than our current models can fully explain. As we lie here, contemplating this cosmic enigma, let us appreciate the beautiful interplay between observation and theory that characterizes modern astronomy. Let us marvel at the fact that a system 6,000 light-years away, invisible to the naked eye, can teach us so much about the fundamental processes that shape our universe. And let us wonder at the mysteries that remain, the questions still unanswered about Cygnus X-1 and the countless other black holes scattered throughout our galaxy and beyond. The black hole that should not exist, yet does. A cosmic riddle wrapped in an enigma, offering challenges and opportunities for those seeking to understand the life cycles of stars and the formation of the most extreme objects in our universe. As we drift towards sleep, let this paradox remind us of the wonders that await discovery and the joy of confronting the unknown with curiosity and an open mind. In the next chapter, we will explore another remarkable aspect of Cygnus X-1, its extraordinary spin, the cosmic whirlpool that makes this black hole not just massive but dynamically extreme, with profound implications for the space-time around it and the processes occurring in its vicinity. But for now, let us simply appreciate the delightful conundrum that is Cygnus X-1, a cosmic object that challenges our understanding by its very existence. The theoretical papers and textbooks said it should not be, yet when we look toward the constellation of the Swan, our instruments detect its unmistakable signature. Theory must bow to observation, and our models must evolve to accommodate this remarkable system. This is the essence of science, the endless dance between what we think we know and what we actually observe, driving us toward a deeper understanding of the cosmos. Cygnus X-1, the black hole that should not exist, yet does, a constant reminder that the universe is under no obligation to conform to our expectations, and all the more fascinating for it. Among the many remarkable features of Cygnus X-1, perhaps the most extraordinary is its spin. The black hole at the heart of this system is rotating at a rate approaching the theoretical maximum allowed by physics. This cosmic whirlpool, twisting the very fabric of space-time around it, is not just an extreme curiosity but has profound implications for the behavior of the system and our understanding of black hole physics. In this chapter, we will explore the nature, measurement, and significance of this extraordinary rotation. To understand the significance of Cygnus X-1's spin, we must first understand what it means for a black hole to rotate. Unlike ordinary objects like planets or stars, a black hole has no surface or material that we can observe directly. What rotates is not matter, but space-time itself, dragged into a swirling motion by the black hole's angular momentum, a phenomenon predicted by Einstein's theory of general relativity. This effect, known as frame dragging or the Lentz-Thirring effect, occurs to some degree around any rotating mass. Even our Earth, spinning on its axis, drags space-time around it ever so slightly. This subtle effect was measured by the Gravity Probe B satellite, which detected a precession of just 4 milliarcseconds per year in the orientation of gyroscopes orbiting Earth, confirming this prediction of general relativity. But around a black hole, particularly one spinning as rapidly as Cygnus X-1, frame dragging becomes dramatic. The rotation creates a region around the black hole called the ergosphere, where space-time is dragged around with such force that nothing, not even light, can remain stationary with respect to distant observers. Any object entering this region is forced to rotate in the same direction as the black hole, an effect that has no analog in our everyday experience. The ergosphere has a unique shape, different from the event horizon beneath it. While the event horizon of a rotating black hole is oblate, flattened at the poles due to the centrifugal force of rotation, the ergosphere extends further outward at the equator. It creates a kind of buffer zone around the black hole, a region where the rotational effects are extreme, but from which escape is still possible. The outer boundary of the ergosphere is called the static limit, the point beyond which it becomes impossible to remain stationary with respect to the distant stars. To visualize this, imagine a stationary observer hovering near a black hole, using powerful rockets to counteract gravity. Outside the static limit, such hovering is possible, although it would require tremendous thrust. But once the observer crosses the static limit and enters the ergosphere, no amount of rocket power can keep them stationary. The frame dragging effect would force them to rotate around the black hole, regardless of how much thrust they applied in the opposite direction. This forced rotation becomes more extreme as one approaches the event horizon. Eventually, at the horizon itself, even light is forced to move in the direction of the black hole's rotation. This is part of what makes the dynamics near a rapidly rotating black hole so different from those around a non-rotating one. The ergosphere extends beyond the event horizon, the boundary from which nothing can escape. This creates a unique region of space, where objects cannot remain stationary, but can still, in principle, escape from the black hole's gravity. Theoretical physicists have speculated that energy could be extracted from a rotating black hole through processes occurring in this region, a topic we will explore later in this chapter. The rotation of a black hole is characterized by a parameter called the spin, often denoted by the letter A. This parameter ranges from 0 for a non-rotating black hole to 1 for a black hole rotating at the maximum possible rate. The spin parameter is a measure of the black hole's angular momentum relative to its mass, scaled in such a way that it cannot exceed 1 without violating physical principles. A spin parameter of exactly 1 would represent a black hole rotating so fast that its event horizon would have to rotate at the speed of light. This is physically impossible according to general relativity, which prohibits any material object or even the fabric of spacetime itself from exceeding light speed. Thus, a spin parameter of 1 represents a theoretical maximum that can be approached but never quite reached in reality. According to measurements made using sophisticated X-ray observations, the spin parameter of Cygnus X-1's black hole is greater than 0.95, possibly as high as 0.98. This means it is rotating at more than 95% of the maximum possible rate, making it one of the most rapidly spinning black holes ever measured. To put this rotation in more familiar terms, consider that a point on the event horizon of this black hole would be moving at a significant fraction of the speed of light. The horizon itself is being stretched by centrifugal forces, causing it to bulge at the equator and flatten at the poles, creating an oblate shape rather than a perfect sphere. For a black hole with the mass of Cygnus X-1, approximately 21 times the mass of our Sun, the event horizon would have a radius of about 60 kilometers if the black hole were not rotating. But because of its rapid rotation, the horizon is flattened to about 30 kilometers at the poles, while the equatorial radius remains close to 60 kilometers. This oblate shape is a direct consequence of the extreme rotation. But how do astronomers measure the spin of an object they cannot see directly? The answer lies in the effects this spin has on the surrounding environment, particularly on the accretion disk of material spiraling into the black hole. Several techniques have been developed to infer black hole spin from these observable effects. One of the most powerful methods is the analysis of the iron K-alpha line in the X-ray spectrum of the accretion disk. Iron atoms in the disk, bombarded by high-energy radiation, emit a characteristic spectral line at a specific energy of about 6.4 keV. But this line appears broadened and skewed in the observed spectrum due to several relativistic effects. First, there is the familiar Doppler effect, which shifts the wavelength of light from material moving toward us to shorter wavelengths, blue shift, and from material moving away from us to longer wavelengths, red shift. Since the disk is rotating, some parts are moving toward us, while others are moving away, creating a broadening of the spectral line. Second, there is the relativistic beaming effect, which makes radiation from material moving toward us appear brighter than from material moving away. This creates an asymmetry in the line profile, enhancing the blue-shifted portion relative to the red-shifted portion. Third, and most distinctively, there is the gravitational redshift, where light loses energy as it climbs out of the black hole's gravitational well. This effect becomes extreme close to the event horizon, creating a characteristic extended tail on the red-shifted side of the line profile. The combination of these three effects, Doppler shifting, relativistic beaming, and gravitational redshift, creates a distinctive asymmetric line profile that astronomers call a relativistic iron line. The precise shape of this line carries information about the gravitational field near the black hole and, crucially, about how close to the event horizon the accretion disk extends. The shape of this iron line profile depends on how close to the black hole the inner edge of the accretion disk extends. For a non-rotating black hole, the innermost stable circular orbit is at 3 times the Schwarzschild radius, the radius of the event horizon. But for a rapidly rotating black hole, this innermost stable orbit moves much closer to the horizon, allowing material to emit radiation from deeper in the gravitational well before plunging into the black hole. For a black hole with the maximum possible spin, the innermost stable orbit would almost coincide with the event horizon itself. This allows material in the accretion disk to approach much closer to the black hole before falling in, experiencing much stronger gravitational effects and producing a more extreme relativistic iron line profile. By analyzing the detailed shape of the iron line profile, astronomers can determine how close to the event horizon the accretion disk extends, which in turn provides a measurement of the black hole's spin. The more extreme the gravitational redshift effects observed in the line profile, the closer the disk must extend to the horizon, and the higher the spin of the black hole. This technique has been applied to Cygnus X-1 using data from several X-ray satellites, including NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton. The results consistently indicate an extremely high spin parameter, placing Cygnus X-1 among the most rapidly rotating black holes known. The iron line method is particularly powerful because it focuses on a specific spectral feature that is relatively easy to identify and isolate from the overall X-ray spectrum. The iron K-alpha line is strong and distinctive, making it a reliable tracer of conditions in the inner accretion disk. However, the method does have some limitations and uncertainties. One complication is that the observed iron line can be affected by factors other than the black hole's spin, such as the inclination of the accretion disk relative to our line of sight, the distribution of iron atoms within the disk, and the presence of outflows or winds that might absorb or scatter some of the radiation. Astronomers must carefully account for these effects when interpreting the line profile. Another method for measuring black hole spin involves analyzing the thermal emission from the accretion disk. The inner regions of the disk are heated to millions of degrees by friction and gravitational compression as material spirals inward. The temperature distribution across the disk depends on where the inner edge is located, which again is determined by the black hole's spin. By fitting theoretical models to the observed thermal spectrum, astronomers can infer the location of the innermost stable orbit and thus the spin of the black hole. This technique, known as the continuum fitting method, has also been applied to Cygnus X-1, yielding results consistent with the iron line analysis. The continuum fitting method requires accurate knowledge of several system parameters, including the black hole's mass, the distance to the system, and the inclination of the accretion disk. Uncertainties in these parameters can affect the spin measurement. However, for Cygnus X-1, these parameters are relatively well constrained from other observations, making the continuum fitting results more reliable. A third approach involves studying quasi-periodic oscillations, or QPOs, in the X-ray output from the accretion disk. These are rhythmic variations in brightness that occur on timescales of milliseconds to seconds. Some QPOs are thought to be related to orbital motions in the innermost regions of the disk, or to resonances between different orbital frequencies. The frequencies of these oscillations depend on the gravitational field near the black hole, which is affected by its spin. By measuring these frequencies and comparing them to theoretical predictions, astronomers can obtain an independent estimate of the spin parameter. While this technique is still being refined, preliminary applications to Cygnus X-1 support the conclusion that it harbors a rapidly rotating black hole. QPOs come in different types, classified by their frequency and other characteristics. High-frequency QPOs, with frequencies of hundreds of hertz, are particularly relevant for spin measurements, as they are thought to originate from the innermost regions of the accretion disk. The specific frequencies at which these oscillations occur can be compared to theoretical models that predict frequencies for various orbital motions near the black hole. For instance, one model suggests that QPOs might be related to the orbital frequency at the innermost stable circular orbit, or to precession frequencies caused by relativistic effects. These frequencies depend on the black hole's mass and spin, so measuring the QPOs allows astronomers to constrain these parameters. The convergence of results from these different methods gives astronomers confidence in the high spin measurement for Cygnus X-1. But what does this extreme rotation mean for the system and for our understanding of black hole physics? One of the most significant implications is the effect on the efficiency of energy release through accretion. As material spirals into a black hole, gravitational potential energy is converted to other forms, primarily heat and radiation. The closer the material can approach before crossing the event horizon, the more energy can be extracted from each unit of mass. For a non-rotating black hole, the theoretical maximum efficiency of this energy conversion is about 6%, meaning that 6% of the rest mass energy of the accreting material can be released. But for a black hole spinning at the rate observed in Cygnus X-1, this efficiency increases to more than 30%. This means that material falling into Cygnus X-1 releases more than 5 times as much energy as it would if the black hole were not spinning. To put this in perspective, nuclear fusion, the process that powers stars like our Sun, converts less than 1% of rest mass to energy. Even nuclear fission, in atomic bombs and power plants, has an efficiency of less than 1%. Accretion onto a rapidly spinning black hole like Cygnus X-1 is thus one of the most efficient energy conversion processes known in the universe, surpassed only by the direct annihilation of matter and antimatter. This enhanced energy release has observable consequences. It contributes to the high X-ray luminosity of Cygnus X-1, making it one of the brightest X-ray sources in our sky, despite its distance of thousands of light years. It also affects the temperature and structure of the accretion disk, potentially influencing the system's behavior during state transitions between different emission regimes. Another important implication of the rapid spin is its effect on the gravitational environment near the black hole. The frame dragging effect creates a region of spacetime, the ergosphere, with unique physical properties. Inside this region, all particles and even light rays are forced to rotate in the same direction as the black hole. This leads to peculiar effects that have no analog in non-rotating systems. One such effect, proposed theoretically but not yet observed, is the Penrose process, named after mathematician Roger Penrose, who first described it in 1969. In this process, an object entering the ergosphere could split in two, with one part falling into the black hole with negative energy, as seen from outside, and the other escaping with more energy than the original object. This would effectively extract energy from the black hole's rotation, reducing its angular momentum slightly. The concept of negative energy might seem strange, but it arises naturally in the mathematics of general relativity applied to rotating black holes. Inside the ergosphere, it's possible for an object to have negative energy relative to an observer at infinity, essentially because the rotational energy of the black hole can be tapped in a way that more than compensates for the object's positive rest mass energy. If the negative energy portion falls into the black hole, it reduces the black hole's mass and angular momentum. Meanwhile, the other portion escapes with more energy than the original object possessed. The extra energy comes from the rotational energy of the black hole. In principle, This process could continue until the black hole's spin is reduced to zero, though in practice, other factors would likely intervene long before this point. While the Penrose process for discrete particles would be difficult to observe, a related phenomenon involving electromagnetic fields, the Blandford-Znajek process, is thought to play a role in powering the relativistic jets observed from systems like Cygnus X-1. In this process, magnetic field lines threading the ergosphere are twisted by the rotating spacetime, creating an electromagnetic torque that extracts energy from the black hole's rotation and channels it into the jets. The Blandford-Znajek process can be thought of as a magnetic version of the Penrose process. Instead of discrete particles entering the ergosphere and splitting, magnetic field lines penetrate this region and become twisted by the rotating spacetime. This twisting generates electrical currents and electromagnetic forces that can accelerate particles to relativistic velocities, forming the jets that are observed emanating from many black hole systems. For Cygnus X-1, with its extremely high spin, the Blandford-Znajek process could be particularly efficient, potentially explaining the power of its jets despite the relatively modest accretion rate compared to some other X-ray binary systems. The energy for these jets would come not primarily from the gravitational energy of the accreting material, but from the vast reservoir of rotational energy stored in the black hole itself. The rapid spin of Cygnus X-1 might help explain the power of its jets, which can accelerate particles to velocities approaching the speed of light and extend for light years from the system. The energy for these jets comes not just from the gravitational energy of falling matter, but potentially also from the rotational energy of the black hole itself, tapped through mechanisms like the Blandford-Znajek process. The extreme spin of Cygnus X-1 also raises questions about how it formed. As we discussed in the previous chapter, black holes are expected to form from the collapsed cores of massive stars. But the cores of such stars typically rotate much more slowly than would be needed to produce a black hole with the observed spin of Cygnus X-1. Throughout a massive star's life, various processes tend to transport angular momentum from the core to the outer layers. These include convection, where hot material rises and cooler material sinks, carrying angular momentum with it, and magnetic coupling between different layers of the star. By the time the star reaches the end of its life, its core is usually rotating relatively slowly. For Cygnus X-1 to have such a high spin, either these angular momentum transport mechanisms were somehow suppressed in its progenitor star, allowing the core to maintain a rapid rotation, or the black hole gained angular momentum after its formation. The latter could occur through the accretion of matter from the companion star, but calculations suggest that the amount of matter accreted over the lifetime of Cygnus X-1 is insufficient to spin up the black hole from a low initial value to the observed rate. A more likely scenario involves the binary nature of the system from its earliest stages. If the progenitor of the black hole was in a close binary configuration with its current companion from the beginning of its life, tidal interactions between the two stars might have affected the internal rotation profile of the progenitor. These interactions tend to synchronize the rotation of the stars with their orbital motion, potentially maintaining a more rapid core rotation than would occur in an isolated star. Additionally, mass transfer between the stars before the formation of the black hole could have affected the angular momentum distribution. If the progenitor star gained mass from its companion early in its life, this could have increased its spin. Alternatively, if it lost mass to the companion through Roche-Lobe overflow, this might have changed its internal structure in ways that affected the core rotation. The exact evolutionary path that led to the formation of such a rapidly spinning black hole remains uncertain. This is another aspect of the Cygnus X-1 puzzle that continues to challenge our understanding of stellar evolution and black hole formation. It's possible that the system represents a relatively rare configuration where conditions were just right to produce an extremely high spin. Recent observations of gravitational waves from merging black holes by LIGO and Virgo have provided some context for understanding the spin of Cygnus X-1. These observations suggest that most stellar mass black holes have relatively low spins, with few approaching the extreme values seen in Cygnus X-1. This supports the idea that Cygnus X-1 is unusual, perhaps representing a special evolutionary pathway rather than the norm for black hole formation. The gravitational wave observations have also revealed a population of black holes more massive than those typically found in X-ray binaries like Cygnus 10-1. Some of these black holes have masses of 30 to 80 solar masses, suggesting that they formed through different pathways, possibly in environments with lower metallicity, where stellar wind mass loss is reduced. The relationship between a black hole's mass and its spin is an area of active research, with Cygnus X-1 providing an important data point as a relatively massive and rapidly spinning black hole. The spin of Cygnus X-1 also has implications for tests of general relativity. Einstein's theory makes specific predictions about how a rapidly rotating black hole affects space-time around it. By studying phenomena near Cygnus X-1, astronomers can test these predictions under conditions of extreme gravity that cannot be reproduced in laboratories on Earth. One prediction is the existence of the innermost stable circular orbit, beyond which stable orbits are impossible due to the effects of general relativity. The location of this orbit depends on the black hole's spin, moving closer to the event horizon as the spin increases. Observations of Cygnus X-1's accretion disk, particularly the iron line profile discussed earlier, confirm the existence and location of this critical orbit, as predicted by general relativity. Another prediction involves the precession of orbits near a rotating black hole. Just as Mercury's orbit precesses due to relativistic effects from the Sun's gravity, an effect that provided one of the early confirmations of general relativity, orbits near Cygnus X-1 should precess much more dramatically due to the stronger gravity and the frame-dragging effect. Certain quasi-periodic oscillations observed in the X-ray output may be related to this precession, providing another test of the theory. The extreme spin of Cygnus X-1 also makes it a valuable laboratory for studying more speculative aspects of black hole physics. For instance, some extensions of general relativity predict deviations from Einstein's theory that would be most apparent in regions of strong gravity and high curvature, such as near the event horizon of a rapidly spinning black hole. Careful observations of phenomena near Cygnus X-1 could potentially reveal or constrain such deviations. Similarly, the interface between general relativity and quantum mechanics, one of the greatest unsolved problems in theoretical physics, might manifest in subtle ways near black hole event horizons. While direct observations of quantum gravitational effects are beyond current capabilities, systems like Cygnus X-1 push our observational techniques to their limits and may eventually provide hints about how these two fundamental theories can be reconciled. Beyond its scientific significance, the extreme spin of Cygnus X-1 invites us to contemplate the nature of rotation in its most extreme form. On Earth, we experience rotation in many contexts, from the daily turning of our planet to the spinning of a top or the whirl of a hurricane. But all these familiar rotations are gentle compared to what occurs near Cygnus X-1. Imagine being near this cosmic whirlpool, where space-time itself is dragged around at a significant fraction of the speed of light, where the very structure of space and time is twisted into configurations with no analog in our everyday experience, where the mathematics of general relativity, usually an abstract formalism for physicists, becomes a tangible reality that determines the fate of every particle and light ray. Such extreme conditions challenge not just our scientific understanding, but our imagination and our intuition. They remind us of the extraordinary diversity of phenomena in our universe, from the gentle rotation of planets to the frenetic spin of a black hole like Cygnus X-1. They invite us to stretch our minds beyond the familiar, to contemplate realities far removed from our everyday experience. As we drift towards sleep, let us appreciate the cosmic ballet playing out thousands of light years away in the constellation of the Swan, a blue supergiant star orbiting with a black hole spinning at nearly the maximum rate allowed by physics. Matter streaming from the star to the black hole, heating to millions of degrees as it spirals through the twisted spacetime near the event horizon. Energy extracted from this maelstrom, powering jets that extend far beyond the binary system. Cygnus X-1, with its extraordinary spin, offers us a glimpse of nature at its most extreme, a reminder that the universe is not just stranger than we imagine, but perhaps stranger than we can imagine. Yet through patient observation, careful analysis, and the framework of general relativity, we have begun to comprehend even such extreme phenomena. In the next chapter, we will explore what Cygnus X-1 can teach us about the formation of black holes throughout cosmic history. But for now, let us marvel at this cosmic spinner, twirling space-time around it in a gravitational dance that has continued for millions of years and will persist long after our brief human civilization has passed from the cosmic stage. Cygnus X-1, spinning faster than anything known in our corner of the universe. A cosmic whirlpool that challenges our understanding and expands our appreciation of the extraordinary phenomena that exist in the vastness of space, have provided some context for understanding the spin of Cygnus X-1. These observations suggest that most stellar mass black holes have relatively low spins, with few approaching the extreme values seen in Cygnus X. This supports the idea that Cygnus X-1 is unusual, perhaps representing a special evolutionary pathway rather than the norm for black hole formation. The spin of Cygnus X-1 also has implications for tests of general relativity. Einstein's theory makes specific predictions about how a rapidly rotating black hole affects spacetime around it. By studying phenomena near Cygnus X-1, astronomers can test these predictions under conditions of extreme gravity that cannot be reproduced in laboratories on Earth. One prediction is the existence of the innermost stable circular orbit, beyond which stable orbits are impossible due to the effects of general relativity. The location of this orbit depends on the black hole's spin, moving closer to the event horizon as the spin increases. Observations of Cygnus X-1's accretion disk, particularly the iron line profile discussed earlier, confirm the existence and location of this critical orbit as predicted by general relativity. Another prediction involves the precession of orbits near a rotating black hole. Just as Mercury's orbit precesses due to relativistic effects from the Sun's gravity, an effect that provided one of the early confirmations of general relativity, orbits near Cygnus X-1 should precess much more dramatically due to the stronger gravity and the frame dragging effect. Certain quasi-periodic oscillations observed in the X-ray output may be related to this precession, providing another test of the theory. The extreme spin of Cygnus X-1 also makes it a valuable laboratory for studying more speculative aspects of black hole physics. For instance, some extensions of general relativity predict deviations from Einstein's theory that would be most apparent in regions of strong gravity and high curvature, such as near the event horizon of a rapidly spinning black hole. Careful observations of phenomena near Cygnus X-1 could potentially reveal or constrain such deviations. Similarly, the interface between general relativity and quantum mechanics, one of the greatest unsolved problems in theoretical physics, might manifest in subtle ways near black hole event horizons. While direct observations of quantum gravitational effects are beyond current capabilities, systems like Cygnus X-1 push our observational techniques to their limits and may eventually provide hints about how these two fundamental theories can be reconciled. Beyond its scientific significance, the extreme spin of Cygnus X-1 invites us to contemplate the nature of rotation in its most extreme form. On Earth, we experience rotation in many contexts, from the daily turning of our planet to the spinning of a top or the whirl of a hurricane. But all these familiar rotations are gentle compared to what occurs near Cygnus X-1. Imagine being near this cosmic whirlpool, where space-time itself is dragged around at a significant fraction of the speed of light, where the very structure of space and time is twisted into configurations with no analog in our everyday experience, where the mathematics of general relativity, usually an abstract formalism for physicists, becomes a tangible reality that determines the fate of every particle and light ray. Such extreme conditions challenge not just our scientific understanding, but our imagination and our intuition. They remind us of the extraordinary diversity of phenomena in our universe, from the gentle rotation of planets to the frenetic spin of a black hole like Cygnus X-1. They invite us to stretch our minds beyond the familiar, to contemplate realities far removed from our everyday experience. As we drift towards sleep, let us appreciate the cosmic ballet playing out thousands of light years away in the constellation of the Swan, a blue supergiant star orbiting with a black hole spinning at nearly the maximum rate allowed by physics. Matter streaming from the star to the black hole, heating to millions of degrees as it spirals through the twisted spacetime near the event horizon. Energy extracted from this maelstrom, powering jets that extend far beyond the binary system. Cygnus X-1, with its extraordinary spin, offers us a glimpse of nature at its most extreme, a reminder that the universe is not just stranger than we imagine, but perhaps stranger than we can imagine. Yet through patient observation, careful analysis, and the framework of general relativity, we have begun to comprehend even such extreme phenomena. In the next chapter, we will explore what Cygnus X-1 can teach us about the formation of black holes throughout cosmic history. But for now, let us marvel at this cosmic spinner, twirling space-time around it in a gravitational dance that has continued for millions of years and will persist long after our brief human civilization has passed from the cosmic stage. Cygnus X-1, spinning faster than anything known in our corner of the universe. A cosmic whirlpool that challenges our understanding and expands our appreciation of the extraordinary phenomena that exist in the vastness of space. As we continue our exploration of Cygnus X-1, let us turn our attention to what this remarkable system can teach us about black hole formation more broadly. The puzzles and peculiarities of Cygnus X-1 that we've explored in previous chapters are not just interesting in their own right, but provide valuable clues about how black holes form throughout the universe and across cosmic time. In this chapter, we will use Cygnus X-1 as a starting point to explore the grand narrative of black hole formation, from the deaths of the first stars to the present day. Black holes come in at least three distinct size classes. Stellar mass black holes, like the one in Cygnus X-1, have masses ranging from a few to perhaps 100 times the mass of our Sun. Intermediate mass black holes, still somewhat elusive, but increasingly supported by observations, range from hundreds to tens of thousands of solar masses. And supermassive black holes, residing at the centers of galaxies, can reach millions or billions of solar masses. Our focus in this chapter will be primarily on stellar mass black holes, the class to which Cygnus X-1 belongs. These are formed from the deaths of massive stars, in processes that take place throughout galaxies like our own. By understanding how the black hole in Cygnus X-1 formed, we gain insights into a population of objects that number perhaps millions in our galaxy alone. Let us begin by considering the standard model of stellar mass black hole formation. According to this model, black holes form from the collapsed cores of massive stars, typically those with initial masses greater than about 25 solar masses. When such a star exhausts its nuclear fuel, the outward pressure that had been supporting it against gravity disappears. The core collapses catastrophically, while the outer layers are expelled in a supernova explosion. If the core has sufficient mass, typically more than about 3 solar masses, no known force can halt its collapse. Neutron degeneracy pressure, which can support the remnants of less massive stars as neutron stars, is overwhelmed by gravity. The core continues to collapse, forming a black hole. This basic picture serves as a starting point, but the details are complex and not fully understood. The actual process depends on many factors, including the star's initial mass, its metallicity, the abundance of elements heavier than helium, its rotation, the presence of magnetic fields, and whether it exists in isolation or as part of a binary system. Cygnus X-1, with its peculiarities that we've explored in previous chapters, challenges aspects of this standard model and provides clues to refine our understanding. Let's examine several key aspects of black hole formation through the lens of Cygnus X-1. The first clue concerns the role of stellar winds in determining the final mass of a black hole. As we discussed in Chapter 6, the black hole in Cygnus X-1 is more massive than we might expect based on standard models of stellar evolution. At 21 solar masses, it retains a significant fraction of its progenitor star's initial mass, despite the strong stellar winds that should have stripped away much of this material before the star's death. This discrepancy suggests that our understanding of mass loss in massive stars may need revision. Perhaps the relationship between metallicity and wind strength is more complex than previously thought. Stars with higher metallicity have more atoms with complex electron structures that can absorb radiation and drive stronger winds. But other factors, such as the star's rotation and magnetic fields, might also play important roles. Recent theoretical work suggests that magnetic fields might confine or channel stellar winds, reducing the overall mass loss. Rapid rotation can affect the distribution of material within the star, potentially altering both the rate of mass loss and the final fate of the core. And binary interactions, as we'll discuss shortly, can significantly complicate this picture. The case of Cygnus X-1 suggests that under certain conditions, massive stars can retain more of their mass than our standard models predict, leading to the formation of more massive black holes. This insight helps explain the range of black hole masses observed in our galaxy and beyond. The second clue from Cygnus X-1 relates to the mechanism of black hole formation. As we explored in Chapter 6, the nearly circular orbit of the binary system suggests that the black hole formed without a powerful, symmetric supernova explosion. Such an explosion would have disrupted the orbit or, at minimum, left it highly eccentric. This points to alternative formation mechanisms, such as direct collapse or a failed supernova. In these scenarios, the core of the massive star collapses directly to a black hole without the dramatic expulsion of the outer layers characteristic of a successful supernova. Much of the star's material falls back onto the newly formed black hole, contributing to its relatively high mass. Recent theoretical and observational work suggests that such failed supernovae might be relatively common, especially for very massive stars. When the core collapses to form a black hole, it might happen so quickly that a shockwave fails to develop or is too weak to expel the outer layers of the star. The entire star essentially disappears, collapsing into the black hole with minimal fireworks. This mechanism helps explain not only the orbital characteristics of Cygnus X-1, but also the apparent gap in the mass distribution of stellar remnants. Observations suggest a scarcity of remnants with masses between about 2 and 5 solar masses, a range that spans the upper limit for neutron stars and the lower limit for black holes. This gap might reflect different formation mechanisms, with neutron stars forming through successful supernovae and black holes through failed supernovae or direct collapse. The third clue from Cygnus X-1 involves the role of binary interactions in black hole formation. The black hole in Cygnus X-1 exists in a close binary system with a massive companion star. This is not a coincidence, but likely played a crucial role in the black hole's formation and evolution. Many massive stars exist in binary or multiple systems. In our galaxy, the majority of stars massive enough to form black holes have at least one companion. These companions can significantly affect the evolution of both stars through tidal interactions, mass transfer, and even mergers. In the case of Cygnus X-1, the progenitor of the black hole and its companion star likely evolved together from the beginning. They may have exchanged mass during their evolution, with material flowing from one star to the other as they expanded during different phases of their lives. These exchanges can alter the evolutionary paths of both stars in complex ways. For instance, if the progenitor of the black hole transferred mass to its companion early in its evolution, this might have reduced its mass, potentially leading to a less violent end. Conversely, if it gained mass from the companion, this could have accelerated its evolution toward a black hole. The specific sequence of mass transfer episodes, their timing, and their rates all affect the final outcome. Binary interactions might also help explain the high spin of Cygnus X-1's black hole. As we discussed in the previous chapter, tidal forces between the two stars could have maintained a rapid rotation in the progenitor star, which was then inherited by the black hole upon collapse. Alternatively, the black hole might have been spun up by accreting material from its companion after formation, though calculations suggest this mechanism alone might be insufficient to explain the observed spin. The importance of binary interactions in black hole formation extends beyond Cygnus X-1. Many of the stellar mass black holes we've discovered exist in binary systems, often with ordinary stars as companions. These systems allow us to detect and study the black holes through the effects they have on their companions, such as X-ray emission from accretion. But this observational bias raises a question: are most black holes in binaries, or do we only detect those that are? The answer has implications for estimating the total population of black holes in our galaxy. If the binary fraction among black hole progenitors is similar to that of massive stars in general, about 70%, and if these binaries tend to survive the black hole formation process, then most black holes might indeed have companions. However, the survival of the binary depends on the details of the black hole formation process. A powerful, symmetric supernova explosion would likely disrupt many systems, especially if more than half the total mass is lost. The fact that we observe systems like Cygnus X-1 suggests that at least some black holes form through less disruptive mechanisms, allowing their binary configurations to survive. The fourth clue from Cygnus X-1 relates to the cosmic evolution of black hole formation. The peculiarities of this system, particularly the high mass of the black hole, might reflect the conditions of star formation at the time and location of its birth. The universe has evolved chemically over cosmic time. The first generation of stars formed from pristine material, containing only hydrogen, helium, and trace amounts of lithium produced in the Big Bang. These stars, sometimes called population 3 stars, would have had very weak stellar winds due to the absence of heavier elements. When they died, they likely left behind relatively massive black holes. As stars lived and died, they enriched the interstellar medium with heavier elements forged in their cores and during supernova explosions. Subsequent generations of stars formed from this enriched material, with increasing metallicity over cosmic time. These higher metallicity stars typically have stronger stellar winds and lose more mass during their lives, leading to the formation of less massive black holes. Cygnus X-1, with its relatively massive black hole despite forming in the disk of our galaxy where metallicity is generally high, might represent an intermediate case. Perhaps it formed in a region with lower than average metallicity, or perhaps other factors, such as binary interactions, offset the effects of metallicity on mass loss. Understanding these variations in black hole formation across cosmic time and different environments is crucial for interpreting observations of black holes throughout the universe. For instance, the black holes detected through gravitational waves by LIGO and Virgo include some with masses significantly higher than those typically found in X-ray binaries in our galaxy. This might reflect formation in environments with lower metallicity, either in the distant past or in regions of the current universe where star formation is occurring in less chemically enriched material. The fifth clue from Cygnus X-1 concerns the relationship between black hole formation and gamma-ray bursts. Gamma-ray bursts are among the most energetic events in the universe, brief but intense flashes of gamma rays that can outshine entire galaxies. Some of these bursts, particularly those lasting more than a few seconds, are associated with the deaths of massive stars and the formation of black holes. The connection arises because the same processes that can lead to black hole formation, particularly in rapidly rotating massive stars, can also produce the conditions needed for a gamma-ray burst. When such a star collapses, it might form a black hole surrounded by a rapidly spinning accretion disk. This configuration can launch jets of material along the rotation axis, which produce the observed gamma-ray emission. The high spin of Cygnus X-1's black hole suggests its progenitor was also rapidly rotating, potentially similar to the progenitors of long gamma-ray bursts. Yet we have no evidence that the formation of Cygnus X-1's black hole was accompanied by such a burst. This discrepancy provides clues about the additional factors, beyond rapid rotation, that might be necessary for gamma-ray burst production. One possibility is that the progenitor of Cygnus X-1's black hole, while rapidly rotating, lacked the strong magnetic fields that are thought to be crucial for launching the powerful jets associated with gamma-ray bursts. Another is that the presence of the companion star somehow affected the collapse process, perhaps disrupting the formation of jets or channeling energy in different ways. Understanding these distinctions helps refine our models of both black hole formation and gamma-ray burst production, two phenomena that represent extreme endpoints of stellar evolution. The sixth clue from Cygnus X-1 relates to the formation of black hole binaries that eventually merge, producing gravitational waves. Since 2015, the LIGO and Virgo gravitational wave observatories have detected dozens of mergers of binary black holes, providing a new window into the black hole population. These merging binaries must have evolved through a complex sequence of events. The simplest pathway involves a binary star system where both stars are massive enough to form black holes. After both have collapsed, the resulting binary black hole system loses energy through gravitational wave emission, causing the orbit to shrink until the black holes merge. However, the initial separation of the stars in such a binary would typically be too large for the black holes to merge within the age of the universe. Some mechanism must bring them closer together. One possibility is common envelope evolution, where one star expands to engulf its companion, creating drag that shrinks the orbit dramatically. Cygnus X-1 represents a different type of black hole binary, one where only one component has collapsed to a black hole, while the other remains a star. Yet it provides insights into the early stages of evolution that might lead to the formation of binary black holes. The close orbit of Cygnus X-1 shows that binary systems can survive the formation of at least one black hole, maintaining or even reducing their separation. When the companion star in Cygnus X-1 reaches the end of its life, it too will collapse. Depending on its final mass, it might form a second black hole, creating a binary black hole system. If the orbit is sufficiently tight at that point, the system might eventually merge due to gravitational wave emission, producing an event detectable by future generations of gravitational wave observatories. By studying systems like Cygnus X-1, astronomers can better understand the pathways that lead to the formation of merging binary black holes, improving predictions for the rate and characteristics of gravitational wave events. The seventh clue from Cygnus X-1 concerns the initial mass function of stars, the distribution of masses with which stars form. This function is crucial for understanding stellar populations and their evolution, including the formation rate of black holes. The existence of a system like Cygnus X-1, with a black hole of 21 solar masses and a companion star of about 40 solar masses, tells us that stars can indeed form at these high masses. Moreover, the binary nature of the system suggests that such massive stars commonly form in pairs. This supports models of star formation, where the initial mass function extends to high masses, perhaps 50 or even 100 solar masses, and where binary formation is a common outcome of the star formation process, especially for massive stars. Understanding the upper end of the initial mass function is challenging because such massive stars are rare and short-lived. Systems like Cygnus X-1 provide valuable data points, helping to constrain this function and its variation across different environments. The eighth and final clue from Cygnus X-1 that we will explore relates to the connection between stellar mass black holes and their supermassive cousins. Supermassive black holes, with masses of millions to billions of solar masses, reside at the centers of most large galaxies, including our own Milky Way. How these giants form remains one of the great unsolved problems in astrophysics. One hypothesis is that they grow from seed black holes, which could be stellar mass black holes that formed from the first generation of stars. These seeds would then grow through accretion of gas and mergers with other black holes, eventually reaching supermassive status. Alternatively, supermassive black holes might form more directly through the collapse of massive gas clouds in the early universe, bypassing the stellar mass black hole stage entirely. The properties of stellar mass black holes like the one in Cygnus X-1 provide context for these scenarios. By understanding how stellar mass black holes form and evolve, we can better assess whether they are plausible progenitors for supermassive black holes. The high mass and spin of Cygnus X-1's black hole, for instance, suggests that stellar evolution can indeed produce black holes with significant mass and angular momentum, potentially suitable as seeds for further growth. Moreover, the binary nature of systems like Cygnus X-1 provides a mechanism for black holes to grow through mergers, which might play a role in the evolution toward intermediate and eventually supermassive black holes. As we reflect on these clues, we see that Cygnus X-1 serves as a Rosetta Stone for understanding black hole formation. Its peculiarities and challenges to standard models force us to refine and expand our understanding of how black holes form and evolve. By studying this single system in detail, we gain insights that help interpret the broader population of black holes throughout the universe. Yet many questions remain. How common are systems like Cygnus X-1? What is the full range of formation pathways for stellar mass black holes? How do these pathways vary with cosmic time and environment? What determines whether a massive star forms a neutron star or a black hole? How are the properties of the black hole, such as its mass and spin, connected to the properties of its progenitor star? Answering these questions requires continued observation and theoretical work. Future telescopes, both in space and on the ground, will provide even more detailed views of systems like Cygnus X-1. Gravitational wave observatories will detect more black hole mergers, revealing the population of binary black holes. And advanced computer simulations will help connect these observations to models of stellar evolution and black hole formation. As we drift towards sleep, let us appreciate the cosmic story encoded in Cygnus X-1. A story that begins with the birth of massive stars from clouds of gas and dust, continues through complex evolutionary pathways shaped by nuclear fusion, stellar winds, and binary interactions, and culminates in the formation of a black hole that continues to interact with its environment, accreting matter and emitting energy that we can detect across thousands of light-years of space. This story is ongoing, The black hole and its companion star continue their cosmic dance, and astronomers continue to study this system, extracting ever more detailed information about its properties and history. Each new observation and theoretical insight brings us closer to a complete understanding of how black holes form and evolve, one of the central questions in modern astrophysics. Cygnus X-1, the first confirmed black hole, remains at the forefront of this scientific journey, a cosmic laboratory for studying the extreme endpoints of stellar evolution and the formation of the most enigmatic objects in our universe. As we conclude this chapter, let us carry with us the realization that the clues to understanding black hole formation are written in the light that reaches us from distant binary systems, in the gravitational waves that ripple through space-time when black holes merge, and in the complex interplay between observation and theory that characterizes modern astronomy. Cygnus X-1, with its peculiarities and challenges to standard models, continues to illuminate this path of discovery, guiding us toward a deeper understanding of the dark giants that populate our universe. In previous chapters, we've explored the discovery of Cygnus X-1, its confirmation as a black hole, and the many puzzles it presents to our understanding of stellar evolution and black hole formation. Now, let us turn our attention to how astronomers study this remarkable system today. What instruments and techniques do they use? What new insights have recent observations revealed? And what questions remain to be answered about this cosmic enigma? Since its discovery in the 1960s, Cygnus X-1 has been observed across the electromagnetic spectrum, from radio waves to gamma rays. Each wavelength regime provides different information about the system, building up a comprehensive picture that no single observation could provide. Modern astronomy is inherently multi-wavelength, combining data from various instruments to extract the maximum possible information about celestial objects. Let us begin our exploration of contemporary studies of Cygnus X-1 with X-ray observations, which remain fundamental to understanding this system, just as they were crucial to its discovery. Today, several space-based X-ray observatories regularly monitor Cygnus X-1, each with its own capabilities and focus. NASA's Chandra X-ray Observatory, launched in 1999, provides the highest spatial resolution of any X-ray telescope ever built. While this resolution is not strictly necessary for studying Cygnus X-1 itself, which appears as a point source even to the most powerful telescopes, it helps to separate the X-ray emission of the black hole from other sources in the crowded region of the Cygnus constellation. Chandra's sharp vision ensures that the X-rays being analyzed truly come from Cygnus X-1 and not from a nearby object. More importantly, Chandra offers excellent spectral resolution, allowing astronomers to precisely measure the energy of incoming X-ray photons. This capability is crucial for analyzing features like the iron K alpha line, which, as we discussed in Chapter 7, provides information about the black hole's spin. By resolving the detailed shape of this line, Chandra helps constrain the properties of the inner accretion disk and the spacetime around the black hole. The European Space Agency's XMM Newton, also launched in 1999, complements Chandra with its large collecting area, which allows it to gather more photons and thus achieve higher sensitivity. This is particularly valuable for studying the rapid variability of Cygnus X-1, including the quasi-periodic oscillations that provide clues about processes occurring near the black hole's event horizon. NASA's Rossi X-ray Timing Explorer, which operated from 1995 to 2012, was specifically designed to study the rapid variability of X-ray sources. Its observations of Cygnus X-1 revealed complex patterns of variability on timescales ranging from milliseconds to months, helping astronomers understand the dynamics of the accretion disk and the processes through which the black hole influences its surroundings. More recent additions to the X-ray astronomy fleet include NASA's Nuclear Spectroscopic Telescope Array, or NuSTAR, launched in 2012, which focuses on higher energy X-rays than its predecessors. These hard X-rays originate from the hottest, innermost regions of the accretion disk and from a corona of energetic particles surrounding the black hole. NuSTAR's observations have provided new insights into the geometry of these regions and the processes that heat them to temperatures of millions of degrees. The most recent major X-ray observatory, NASA's Imaging X-ray Polarimetry Explorer, or IXPE, launched in 2021, adds a new dimension to X-ray studies by measuring not just the energy and arrival time of X-ray photons, but also their polarization, the orientation of their electromagnetic fields. This information helps constrain the geometry of the X-ray emitting regions and the strength and configuration of magnetic fields near the black hole. Together, these X-ray observatories provide a much more detailed view of Cygnus X-1 than was possible during its discovery era. They reveal not just the presence of X-ray emission, but its detailed energy distribution, its variability patterns, and increasingly, its polarization properties. This wealth of data allows astronomers to test sophisticated models of accretion onto black holes and the physical processes that occur in these extreme environments. Moving beyond X-rays, radio observations continue to provide crucial information about Cygnus X-1, particularly regarding its jets. The Very Long Baseline Array, a network of 10 radio telescopes spread across the United States, can resolve details as small as a few milliarc seconds, allowing it to image the structure of the jets emanating from near the black hole. These observations reveal the jets' morphology, their expansion rate, and variations in their intensity over time. The European VLBI network and the Global Event Horizon Telescope Consortium, which combines radio telescopes around the world to function as a single Earth-sized instrument, provide even higher resolution. While these networks are best known for their observations of supermassive black holes, including the first direct image of a black hole's shadow in galaxy M87, they also contribute to our understanding of stellar mass black holes, like Cygnus X-1, by revealing details of their jet structures. Radio observations are particularly valuable for studying the jets, because the radio emission originates primarily from relativistic electrons, spiraling around magnetic field lines in the jets. By analyzing how this emission varies with frequency and time, astronomers can infer the jet's physical properties, including the energy distribution of the electrons, the strength of the magnetic fields, and the jet's velocity. Recent radio observations have shown that the jets from Cygnus X-1 extend for several light-years from the black hole, much farther than previously thought. They have also revealed complex structures within the jets, including knots and bends that might reflect variations in the accretion process or interactions with the surrounding interstellar medium. In the infrared portion of the spectrum, observations focus primarily on the companion star, HDE 226868. Infrared light penetrates dust more effectively than visible light, allowing astronomers to study this star even though it lies in a relatively dusty region of the galaxy. Instruments like NASA's Spitzer Space Telescope, which operated from 2003 to 2020, and its successor, the James Webb Space Telescope, launched in 2021, provide detailed infrared spectra of the companion star. These spectra reveal the star's composition, temperature, and other physical properties. They also show absorption features from the stellar wind, providing information about the mass loss from the companion star that feeds the accretion disk around the black hole. By monitoring how these features change over time, astronomers can track variations in the stellar wind and potentially connect them to changes in the X-ray emission from the accreting black hole. Optical observations, using both ground-based telescopes and space observatories like the Hubble Space Telescope, continue to play an important role in studying Cygnus X-1. The companion star is visible in optical wavelengths, and its spectrum provides crucial information about its orbital motion, which in turn constrains the mass of the black hole. Modern optical spectroscopy, with its high resolution and sensitivity, allows astronomers to measure the companion star's radial velocity, its motion toward or away from us, with extraordinary precision. These measurements, combined with the known orbital period of 5.6 days, provide the most accurate determinations of the black hole's mass. Recent analyses using this technique have refined the mass estimate to 21.2 plus, or minus 2.2 solar masses. Optical observations also reveal absorption lines from the stellar wind, similar to those seen in the infrared, but probing different components of the wind. By comparing these lines with theoretical models, astronomers can determine the wind's velocity structure, its mass loss rate, and its composition. This information is crucial for understanding how material flows from the companion star to the black hole, fueling the accretion process. In the ultraviolet portion of the spectrum, Observations by instruments like the Hubble Space Telescope's Cosmic Origin spectrograph provide additional insights into the companion star's wind and the environment around the black hole. Ultraviolet spectroscopy is particularly sensitive to highly ionized atoms, those that have lost multiple electrons due to the intense radiation near the black hole. The presence and strength of these ionized species help map the temperature and density structure of the gas surrounding the binary system. At the highest energies, gamma-ray observations by satellites like NASA's Fermi Gamma Ray Space Telescope and ground-based facilities like the High Energy Stereoscopic System, or HESS, in Namibia, probe the most energetic processes associated with Cygnus X-1. These observations have detected gamma rays from the system, particularly during periods when its jets are active. The presence of gamma ray emission indicates that particles are being accelerated to extremely high energies, approaching the speed of light. The specific characteristics of this emission, including its energy spectrum and variability, provide clues about the acceleration mechanisms operating in the jets and the maximum energies that particles can achieve in this environment. Beyond electromagnetic observations, gravitational wave astronomy offers a potential new window into systems like Cygnus X-1. While current gravitational wave detectors like LIGO and Virgo are not sensitive to the stable orbits of binary systems like Cygnus X-1, future observatories, particularly space-based ones like the proposed Laser Interferometer Space Antenna, or LISA, might be able to detect the subtle gravitational waves produced by such binaries. These gravitational waves would provide complementary information to electromagnetic observations, directly probing the orbital dynamics of the system and potentially revealing details about the black hole's mass, spin, and even its internal structure, if any deviations from general relativity's predictions exist. Neutrino astronomy, still in its infancy, might also eventually contribute to our understanding of systems like Cygnus X-1. If the jets or accretion disk produce significant numbers of neutrinos, large detectors like IceCube at the South Pole might be able to detect them, providing yet another perspective on the physical processes occurring near the black hole. This multi-messenger approach, combining information from different types of messengers, including electromagnetic waves across the spectrum, gravitational waves, and potentially neutrinos, represents the frontier of astronomical research. Cygnus X-1, as one of the brightest and best-studied black hole systems, will likely be at the forefront of such comprehensive investigations. Having surveyed the observational techniques used to study Cygnus X-1 today, let us turn to some of the key scientific questions that these observations are helping to address. Despite decades of study, many aspects of this system remain incompletely understood, driving ongoing research and occasional revisions to our understanding. One fundamental question concerns the detailed structure of the accretion flow near the black hole. The standard model involves a thin, optically thick accretion disk extending close to the black hole when the system is in its soft state, and a thicker, optically thin flow, possibly with a central cavity, when in its hard state. But the real situation may be more complex, with multiple components coexisting and evolving as the system transitions between states. Recent observations, particularly with NuSTAR and IXP, are providing new constraints on this structure. The polarization measurements from IXPE are especially valuable, as they directly probe the geometry of the X-ray emitting regions. Preliminary results suggest that the corona, the hot, diffuse region above the accretion disk that produces high-energy X-rays, may be more compact and closer to the black hole than some models had suggested. Another active area of research concerns the connection between the accretion disk and the jets. When Cygnus X-1 transitions from its soft to its hard state, the jets strengthen dramatically, suggesting a close relationship between the accretion flow configuration and jet formation. But the exact mechanism linking these phenomena remains uncertain. One hypothesis involves the magnetic field structure near the black hole. As the inner accretion disk recedes or becomes less dense during the transition to the hard state, the magnetic field configuration might change in ways that favor jet formation. Contemporary observations across multiple wavelengths, timed to catch Cygnus X-1 during these transitions, are helping to test this idea by tracking the evolution of both the disk and the jets. The origin and evolution of the corona also remain poorly understood. This region of hot, energetic particles plays a crucial role in producing the high-energy X-rays observed from Cygnus X-1. particularly in its hard state. But what heats the corona to temperatures of millions of degrees, and what determines its size, shape, and density? Some models suggest that magnetic reconnection, the same process that powers solar flares on our sun, might heat the corona. Others propose that it forms from material evaporated from the accretion disk by intense radiation. The detailed energy spectrum and polarization of X-rays from Cygnus X-1, as measured by current observatories, are providing new constraints on these models, gradually narrowing down the possibilities. The companion star, HDE 226868, raises its own set of questions. How long will it continue in its current evolutionary state before exhausting its nuclear fuel? When it does evolve further, how will this affect the binary system? Will it eventually explode as a supernova, potentially forming a second black hole? Or might it lose its outer layers more gradually, perhaps through Roche-Lobe overflow onto the existing black hole? Detailed spectroscopy of the companion star, combined with theoretical models of stellar evolution, helps address these questions. Recent analyses suggest that the star is currently in a phase where it's transitioning from core hydrogen burning to core helium burning, a relatively brief but stable state. This suggests that the current configuration of Cygnus X-1 might persist for perhaps a few 100,000 years, a blink of an eye in cosmic terms, but long enough for continued human observation. The future evolution of the system is less certain and depends on the detailed mass transfer history between the two components. Some models suggest that the companion star might lose enough mass to avoid a supernova explosion, instead becoming a white dwarf or a lower mass neutron star. Others indicate that it might still retain enough mass to explode as a supernova, potentially disrupting the binary or leaving behind a second black hole. This latter scenario is particularly intriguing from a gravitational wave perspective. If Cygnus X-1 eventually becomes a binary black hole system, it might, after billions of years of orbital decay due to gravitational wave emission, merge in an event similar to those detected by LIGO and Virgo. While we won't be around to witness this distant future event, understanding the evolutionary trajectory of systems like Cygnus X-1 helps predict the rate and characteristics of black hole mergers throughout the universe. Beyond these specific questions about Cygnus X-1, the system serves as a laboratory for testing fundamental physics under extreme conditions. The strong gravitational field near the black hole provides opportunities to test Einstein's theory of general relativity in regimes where alternative theories might predict deviations. The high temperatures and densities in the accretion disk and corona allow studies of plasma physics under conditions impossible to recreate in terrestrial laboratories. For instance, the ion line profile and quasi-periodic oscillations from the inner accretion disk directly probe the space-time geometry very close to the black hole. Any deviations from the predictions of general relativity would appear as anomalies in these observations. So far, all measurements are consistent with Einstein's theory, but more precise observations might eventually reveal subtle differences, pointing toward a more complete theory of gravity. Similarly, the behavior of magnetized plasma in the accretion disk and jets can be compared with theoretical models and computer simulations. The complex interplay between gravity, radiation, and magnetic fields in these environments challenges our computational capabilities, but also provides opportunities to refine our understanding of these fundamental processes. Looking to the future, several planned observatories will enhance our ability to study Cygnus X-1 and similar systems. The European Space Agency's Athena X-ray Observatory, scheduled for launch in the 2030s, will combine high spectral resolution with large collecting area, allowing even more detailed studies of the accretion flow. NASA's proposed Lynx X-ray Observatory would provide complementary capabilities, with emphasis on high spatial resolution imaging and sensitive spectroscopy. In the radio regime, the next-generation Very Large Array will provide enhanced sensitivity and resolution for studying the jets from Cygnus X-1. And in the gravitational wave field, space-based observatories like LISA will open a new window on binary systems, potentially including Cygnus X-1 itself. These future facilities, combined with continued observations using current instruments and ongoing theoretical work, ensure that Cygnus X-1 will remain at the forefront of astronomical research for decades to come. Each new observation adds to our understanding of this remarkable system and, by extension, to our knowledge of black holes, stellar evolution, and the extreme physics of accretion. As we contemplate the ongoing study of Cygnus X-1, it's worth reflecting on the remarkable progress since its discovery. From a mysterious X-ray source detected by early rocket flights, to a comprehensively studied black hole binary whose properties are known in exquisite detail, Cygnus X-1 exemplifies the power of persistent scientific inquiry. Each generation of astronomers has built upon the work of their predecessors, gradually unveiling the nature of this cosmic enigma. The story of Cygnus X-1 is not just about a single astronomical object, but about the development of an entire field. X-ray astronomy, relativistic astrophysics, accretion theory, and black hole physics have all advanced in parallel with our understanding of this system. Cygnus X-1 has served as both a driver of theoretical development and a testing ground for new ideas and models. As we drift towards sleep, let us appreciate the ongoing dialogue between observation and theory that characterizes the study of Cygnus X-1. Observations reveal new complexities that challenge existing models, spurring theorists to develop more sophisticated explanations. These new models, in turn, make predictions that can be tested with the next generation of observations, continuing the cycle of scientific progress. Cygnus X-1, the first confirmed black hole, continues to illuminate our understanding of these most extreme objects in the universe. From its vantage point, 6,000 light-years away in the constellation of the Swan, it sends us messages encoded in light across the electromagnetic spectrum, messages that we are increasingly able to decipher as our technological capabilities and theoretical understanding advance. In the next chapter, we will explore why Cygnus X-1 still matters, not just as a scientific object, but as a cultural icon that has influenced our collective imagination and our conception of the cosmos. But for now, let us marvel at the sophisticated techniques and instruments that allow us to study this distant black hole, and at the dedicated scientists who continue to unravel its secrets. 6 decades after its initial discovery, as we approach the final chapters of our exploration of Cygnus X-1, it is worth pausing to consider why this particular black hole continues to matter, not just to astronomers, but to our broader understanding of the universe and our place within it. More than 50 years after its discovery, Cygnus X-1 remains a cornerstone of astrophysics, a touchstone for our understanding of extreme cosmic phenomena, and a cultural icon that has influenced how we think about black holes in general. In this chapter, we will explore the enduring significance of this remarkable object across multiple dimensions. First and foremost, Cygnus X-1 matters because it was the first. As the first confirmed black hole, it transformed these objects from theoretical curiosities to observational realities. Before Cygnus X-1, black holes existed only in the equations of general relativity and the imaginations of theorists. After its confirmation, they became concrete astrophysical objects that could be studied, categorized, and understood as a fundamental component of our universe. This transition from theory to observation is a crucial step in the scientific process. Mathematical predictions, no matter how elegant, remain tentative until confronted with empirical evidence. Einstein's theory of general relativity, published in 1915, allowed for the possibility of black holes. Carl Schwarzschild derived the mathematical solution describing a non-rotating black hole just months later. But for decades, these solutions were regarded by many, including Einstein himself, as mathematical artifacts rather than physical realities. The discovery and confirmation of Cygnus X-1 changed this perception irrevocably. It demonstrated that the extreme predictions of general relativity, including the formation of event horizons from which nothing, not even light, can escape, were not merely theoretical abstractions but descriptions of actual objects in our galaxy. This validation of theory by observation strengthened confidence in general relativity and established black holes as essential components of the cosmic inventory. As the prototype for stellar mass black holes, Cygnus X-1 continues to serve as a benchmark against which other systems are compared. When astronomers discover a new black hole candidate, they often analyze it using techniques and models refined through the study of Cygnus X-1. Its well-constrained parameters, including its mass, spin, and orbital characteristics, provide a reference point for understanding the broader population of black holes in our galaxy and beyond. This role as a standard candle, so to speak, for black hole studies has been particularly valuable as the known population of these objects has expanded. From the handful of black hole candidates known in the 1970s, the catalogue has grown to include dozens of confirmed stellar mass black holes in X-ray binaries, hundreds detected through gravitational waves, and thousands of candidates identified through other means. Throughout this expansion of our black hole census, Cygnus X-1 has remained the most thoroughly studied example, the foundation upon which our understanding of the broader population is built. Beyond its historical primacy and ongoing role as a reference system, Cygnus X-1 matters because it continues to challenge and refine our theories of stellar evolution and black hole formation. As we explored in Chapter 6, the existence of Cygnus X-1 in its current form poses puzzles for standard models. Its high mass, rapid spin, and nearly circular orbit all suggest formation pathways that differ from the simplest scenarios of stellar collapse and supernova explosions. These challenges to conventional wisdom have stimulated theoretical work on alternative formation mechanisms, including direct collapse, failed supernovae, and complex binary interactions. The continued study of Cygnus X-1 and similar systems has led to a more nuanced understanding of the diverse ways in which black holes can form, evolve, and interact with their environments. Rather than a single universal pathway from massive star to black hole, we now recognize a variety of routes influenced by factors such as metallicity, rotation, binary interactions, and magnetic fields. This more sophisticated understanding extends beyond black hole formation to encompass broader questions of stellar evolution. The companion star in Cygnus X-1, HDE 226868, provides an opportunity to study how massive stars evolve in binary systems, where interactions with a compact companion can significantly alter their life trajectories. The mass transfer from this star to the black hole, observable through multiple wavelengths, offers a window into processes that are central to the evolution of many binary systems throughout the universe. Cygnus X-1 also matters as a laboratory for studying accretion, the process by which black holes and other compact objects gather material from their surroundings. Accretion is one of the most energetic processes in the universe, converting gravitational potential energy into radiation with efficiencies that can exceed those of nuclear fusion. It powers not just stellar mass black hole systems like Cygnus X-1, but also active galactic nuclei, where supermassive black holes at the centers of galaxies accrete material at prodigious rates. Through detailed observations across the electromagnetic spectrum, astronomers have used Cygnus X-1 to test and refine models of accretion disks, coronae, and jets. The different spectral states observed in this system, transitions between them, and the associated changes in the accretion flow and jet production have provided crucial insights into the complex interplay between gravity, radiation, and magnetic fields in these extreme environments. These insights extend far beyond Cygnus X-1 itself. The physical processes operating in this system are scaled versions of those occurring around supermassive black holes, which can be billions of times more massive. The fundamental physics of accretion, governed by gravity, gas dynamics, and radiation, operates similarly across this vast range of scales. Thus, understanding accretion in Cygnus X-1 helps interpret observations of distant quasars and active galactic nuclei, objects that play crucial roles in the evolution of galaxies and the large-scale structure of the universe. Cygnus X-1 further matters as a natural laboratory for testing fundamental physics under extreme conditions. The region near the black hole's event horizon represents one of the strongest gravitational fields accessible to astronomical observation. By studying phenomena in this region, such as the distortion of the ion emission line by gravitational redshift or the quasi-periodic oscillations from the inner accretion disk, astronomers can test the predictions of general relativity in regimes far beyond what can be achieved in terrestrial experiments. So far, all observations of Cygnus X-1 and similar systems are consistent with Einstein's theory. This consistency reinforces confidence in general relativity, while also constraining alternative theories of gravity. As observational capabilities improve, more precise measurements may eventually reveal subtle deviations from general relativistic predictions, potentially pointing toward a more complete theory that unifies gravity with quantum mechanics. Cygnus X-1, with its well-characterized properties and ongoing observational campaigns, will likely play a role in such tests of fundamental physics. Beyond gravity, The extreme conditions near Cygnus X-1's black hole provide opportunities to study plasma physics, magnetohydrodynamics, and particle acceleration under conditions impossible to recreate in laboratories. The temperatures in the inner accretion disk reach millions of degrees, magnetic fields are twisted and amplified to extraordinary strengths, and particles are accelerated to velocities approaching the speed of light. Studying these processes in Cygnus X-1 contributes to our understanding of high-energy plasma physics, with potential applications ranging from fusion energy research to cosmic ray origins. The significance of Cygnus X-1 extends beyond the realm of natural science to influence how we collectively imagine and conceptualize black holes. As the first confirmed black hole, it played a crucial role in transforming these objects from esoteric mathematical constructs to concrete astrophysical entities in the public consciousness. The name Cygnus X-1 itself has entered popular culture, referenced in science fiction, music, literature, and other cultural expressions. Perhaps the most famous cultural reference to Cygnus X-1 is the song suite by the Canadian rock band Rush, released in 1977. Titled Cygnus X-1, it tells the story of an astronaut deliberately piloting his ship into the black hole, drawn by an irresistible pull, both physical and metaphysical. The lyrics capture both the scientific wonder of these extreme objects and their metaphorical resonance as symbols of the unknown, the inevitable, and the transformative. This cultural significance matters because it reflects and shapes how society at large engages with complex scientific concepts. Black holes have become powerful symbols in our collective imagination, representing mysteries, thresholds, and points of no return. Cygnus X-1, as the original exemplar of these exotic objects, has contributed to this symbolic lexicon, enriching our cultural discourse with concepts from the frontiers of astrophysics. The enduring significance of Cygnus X-1 also lies in what it represents about the scientific enterprise itself. The story of its discovery, confirmation, and ongoing study exemplifies the patient, collaborative, and cumulative nature of scientific progress. From the initial detection by early X-ray instruments to the sophisticated multi-wavelength campaigns of today, generations of astronomers have built upon each other's work, gradually refining our understanding of this system. This process has not been linear or without controversy. The interpretation of Cygnus X-1 as a black hole was initially contested, with alternative explanations proposed and debated. The parameters of the system, including the black hole's mass and spin, have been revised as observational capabilities improved and new analytical techniques were developed. This evolution of understanding illustrates how science advances through continual questioning, testing, and refinement, rather than sudden, definitive revelations. The study of Cygnus X-1 also demonstrates the increasingly collaborative and international nature of modern astronomy. Observational campaigns today might involve multiple telescopes around the world and in space, operated by different countries and agencies, with data analyzed by international teams of scientists. This collaboration transcends political boundaries, united by shared curiosity about the cosmos and commitment to scientific inquiry. Looking toward the future, Cygnus X-1 will likely continue to matter as new observational capabilities and theoretical frameworks emerge. As we discussed in the previous chapter, planned observatories across the electromagnetic spectrum will provide even more detailed views of this system. Future gravitational wave detectors might eventually detect the subtle space-time ripples from the orbital motion of the black hole and its companion. Advanced computer simulations will model the complex physics of the system with increasing fidelity. These future studies will not only refine our understanding of Cygnus X-1 itself, but will contribute to addressing broader questions in astrophysics and fundamental physics. How do massive stars end their lives? What shapes the distribution of black hole masses and spins? How do accretion disks and jets form and evolve? Does general relativity accurately describe gravity under the most extreme conditions? Cygnus X-1, with its rich observational history and well-constrained parameters, will continue to provide context and constraints for addressing these fundamental questions. Beyond its scientific significance, Cygnus X-1 matters because it expands our cosmic perspective. It reminds us that our universe contains phenomena far more extreme than those we encounter in everyday life. Temperatures of millions of degrees, gravitational fields strong enough to bend light into circular orbits, densities so great that all matter is crushed beyond recognition. These are not just theoretical possibilities, but actual conditions existing in our galaxy, not so far from our own stellar neighborhood. This cosmic perspective can be both humbling and inspiring. Humbling because it reminds us of the vastness and extremity of the universe compared to our limited direct experience. Inspiring because it demonstrates our remarkable ability, through careful observation and mathematical reasoning, to understand phenomena far beyond our immediate senses. Cygnus X-1, invisible to the naked eye yet comprehensible through the tools of modern science, exemplifies this capacity to extend our understanding beyond our direct perception. There is also something profound in the realization that we, as a species, have managed to discover and understand objects as extreme as black holes. From our position on a small planet orbiting an ordinary star, we have developed the intellectual and technological capabilities to detect, measure, and comprehend these cosmic enigmas. Cygnus X-1 stands as a testament to human curiosity and ingenuity, to our collective desire to explore and make sense of the universe we inhabit. As we prepare to drift into sleep, let us appreciate the layers of significance that make Cygnus X-1 matter, from its historical primacy as the first confirmed black hole to its ongoing role as a laboratory for extreme physics, from its cultural resonance to its expansion of our cosmic perspective. This system, a dance of a massive star with an invisible partner of extraordinary density, continues to reveal the wonders of our universe and the power of the human mind to comprehend them. In the next chapter, we will explore the symbolism of Cygnus X-1, considering its place in the constellation of the Swan and the mythological and cultural associations it carries. But for now, let us simply appreciate that this black hole, first detected as an anomalous X-ray source decades ago, continues to matter in our ongoing quest to understand the cosmos and our place within it. As we near the conclusion of our journey exploring Cygnus X-1, let us take a different perspective, considering not just the scientific significance of this remarkable black hole, but its symbolic resonance. The name itself, Cygnus X-1, locates this object within the constellation of the Swan, a pattern of stars recognized and mythologized by human cultures for thousands of years. This connection between an ancient constellation, steeped in mythology and cultural meaning, and one of the most extreme objects known to modern science, creates a rich tapestry of symbolism worth exploring as we drift towards sleep. The constellation Cygnus represents a swan flying along the plane of the Milky Way, its wings outstretched across our galaxy's bright band of stars. To ancient Greek observers, this celestial swan was associated with several mythological tales. In one story, it represents Zeus, king of the gods, who transformed himself into a swan to seduce Leda, the queen of Sparta. In another version, it is the form taken by Apollo's son Orpheus after his death, placed among the stars to honor his musical gifts. In other cultures, the cross-like shape of Cygnus suggested different images. To some Native American peoples, it was the Northern Cross, while ancient Chinese astronomers saw it as part of a larger asterism called the Celestial Ford, spanning the river of the Milky Way. Across these varied cultural interpretations, Cygnus has been consistently recognized as a distinctive pattern in the night sky, a fixed reference point in humanity's ongoing relationship with the cosmos. The brightest star in Cygnus, Deneb, marks the tail of the swan. Its name derives from the Arabic word for tail, reflecting the contribution of Arab astronomers to our stellar nomenclature. Deneb is one of the most luminous stars visible to the naked eye, a blue-white supergiant, similar in some ways to HDE 226868, the companion star to Cygnus X-1. At the opposite end of the swan, marking its beak, lies Alboreo, a beautiful double star whose components show contrasting colors of gold and blue when viewed through a telescope. The body of the swan, between these two distinctive stars, contains Cygnus X-1, invisible to human eyes, but revealed through the tools of modern astronomy. This juxtaposition of the visible and the invisible, the ancient and the modern, creates a first layer of symbolism. The same region of sky that has been observed and interpreted by humans throughout recorded history contains an object completely unknown until the advent of X-ray astronomy in the 20th century. The swan, a creature of beauty and grace in many cultural traditions, harbors within its celestial representation one of the most extreme and potentially destructive objects in the cosmos. This contrast between appearance and hidden reality mirrors a broader theme in astronomy and science. The universe, as it appears to our unaided senses, represents only a fraction of what exists. Beyond the visible stars lie planets, nebulae, galaxies, and exotic objects like black holes, revealed only through instruments that extend our perceptual capabilities. Cygnus X-1 symbolizes this extension of human awareness beyond the limitations of our natural senses, our ability to discover and comprehend phenomena that would otherwise remain forever hidden. The swan itself carries rich symbolic associations that resonate with the nature of Cygnus X-1. In many cultures, swans symbolize transformation and transition. In Greek mythology, Zeus transforms into a swan to approach Leda. In the tale of the ugly duckling, the protagonist undergoes a metamorphosis from an awkward, misfit bird to a beautiful swan. This theme of transformation echoes the physical reality of Cygnus X-1, which formed through the transformation of a massive star into a black hole, one of the most dramatic changes possible in the universe. Swans are also frequently associated with duality, embodying both grace and aggression, beauty and power. The elegant appearance of a swan gliding across water conceals powerful legs working beneath the surface. Similarly, the seemingly empty space occupied by Cygnus X-1 conceals an object of extraordinary power and influence, capable of bending light, distorting space-time, and accelerating particles to nearly the speed of light. In some traditions, swans symbolize the journey between worlds. In Celtic mythology, they can travel between the ordinary world and the other world, carrying messages or souls. This resonates with the nature of black holes as thresholds or boundaries in space-time, regions where our current understanding of physics reaches its limits, and where the known laws of nature transform into something beyond our current comprehension. The X in Cygnus X-1 carries its own symbolic weight. As the letter designating the first X-ray source discovered in the constellation, it represents the unknown or the uncharted, as in X marks the spot on treasure maps. This designation became particularly apt when the source was identified as a black hole, perhaps the most mysterious and enigmatic class of objects in the cosmos, regions where space and time as we understand them cease to exist. The number 1 in Cygnus X-1 similarly carries significance beyond its function as a simple catalog designation. As the first confirmed black hole, Cygnus X-1 stands at the beginning of our observational understanding of these objects. This primacy gives it a symbolic status similar to other firsts in scientific discovery, like the first observed planet beyond our solar system or the first detected gravitational wave. These firsts mark transitions from theoretical possibility to observed reality, expanding the boundaries of confirmed knowledge. Together, the elements of the name Cygnus X-1 create a designation that is both scientifically precise and symbolically resonant, locating this object within astronomical catalogues while connecting it to ancient mythologies and universal symbolic patterns. This dual nature reflects the object itself, which exists simultaneously as a physical entity subject to scientific investigation and as a concept that engages our imagination and philosophical reflection. Beyond its name, Cygnus X-1 embodies several powerful symbolic themes that have resonated throughout human culture. Perhaps most prominently, it represents the invisible yet influential forces and entities that shape our world while remaining beyond direct perception. Throughout history, humans have grappled with the reality of unseen influences, from spiritual forces in traditional beliefs to fields and particles in modern physics. Cygnus X-1, detected only through its effects on surrounding matter and energy, exemplifies this theme of hidden causality. This invisibility gives black holes a particular resonance in philosophical discussions about appearance versus reality. What we perceive with our senses, or even with our instruments, may not reflect the fundamental nature of reality. Just as the black hole is known not through direct observation, but through its gravitational effects, many philosophical traditions suggest that the ultimate nature of reality lies beyond our direct perception, accessible only through inference and theoretical construction. Cygnus X-1 also symbolizes the limits of knowledge and the boundaries of the known universe. The event horizon of a black hole represents a threshold beyond which information cannot return to the outside universe. Light, matter, and signals of any kind that cross this boundary are lost to external observers. This absolute boundary in the physical world has served as a powerful metaphor for the limits of human knowledge, the existence of realms beyond our capacity to explore or understand. Yet paradoxically, black holes have also symbolized the drive to push beyond such boundaries, to comprehend even the seemingly incomprehensible. The development of theoretical frameworks to describe black holes, from general relativity to quantum field theory in curved spacetime, represents one of the great intellectual achievements of modern science. Cygnus X-1 stands as a testament to this drive, an object once thought to be beyond the reach of observation now subject to detailed scientific study. In literature, art, and popular culture, black holes in general, and Cygnus X-1 in particular, have served as powerful symbols for a range of concepts. They have represented inevitable fate and inescapable attraction, reflecting their gravitational pull from which nothing, once past the event horizon, can escape. They have symbolized transformation and rebirth, portals to other dimensions or universes, and the ultimate dissolution of form into formlessness. The song suite Cygnus X-1 by Rush, which we mentioned in the previous chapter, exemplifies this cultural symbolism. In the lyrics, the black hole represents both destruction, consuming the protagonist's spacecraft, and transformation, as he merges with the cosmic consciousness represented by the God of Gods. This dual nature, simultaneously destroyer and creator, reflects ancient mythological figures like Shiva in Hindu tradition, or the concept of creative destruction in various philosophical systems. Astronomically, Cygnus X-1 resides in the plane of the Milky Way, the band of light representing the disk of our galaxy when viewed from our position within it. This placement adds another layer of symbolism, situating this extreme object within the broader context of our cosmic home. The Milky Way itself has rich symbolic associations across cultures, often represented as a road, river, or bridge connecting the earthly and celestial realms. In many indigenous traditions, it represents the path taken by souls after death, a journey from the familiar to the unknown. The position of Cygnus X-1 within this mythologically significant band of light creates a symbolic resonance between ancient cosmologies and modern astrophysics. The same region of sky that traditional cultures identified as a pathway between worlds now reveals, through scientific observation, an object that represents a boundary in space-time, a threshold between the physics of everyday experience and regimes where our current theories break down. In a more personal dimension, Cygnus X-1 can serve as a symbol for the hidden depths within ourselves, aspects of our being that influence our thoughts and actions, while remaining largely invisible to conscious awareness. Just as the black hole exerts its pull on surrounding matter while remaining unseen, unconscious drives, desires, and patterns shape our lives, while often eluding direct introspection. The work of understanding these hidden dimensions of ourselves parallels, in some ways, the scientific effort to comprehend black holes through their observable effects. For those who ponder existential questions, black holes like Cygnus X-1 can symbolize the inevitable entropy that awaits all structures in the universe. According to current understanding, even black holes will eventually evaporate through Hawking radiation, though for stellar mass black holes this process would take unimaginably long timescales, far beyond the current age of the universe. This ultimate fate reflects philosophical themes of impermanence and transience, found in traditions from Buddhism to existentialism. Yet within this cosmic transience, there is also a kind of permanence. Once matter crosses the event horizon of Cygnus X-1, its information, in some form, becomes encoded on the horizon itself, according to current theoretical understanding. This encoding, while transformed beyond recognition from its original state, preserves something of what has fallen in. This tension between transformation and conservation echoes philosophical questions about identity, continuity, and the nature of change. For astronomers and physicists who study objects like Cygnus X-1, these symbolic dimensions may seem secondary to the scientific reality. Yet the human mind naturally works with symbols and metaphors, even in the most rigorous scientific contexts. The conceptual frameworks we use to understand black holes, the mathematics we employ to describe them, and the language we use to discuss them all engage our symbolic capacities alongside our analytical ones. The enduring fascination with black holes in both scientific research and popular culture stems partly from this rich symbolic resonance. Cygnus X-1 is simultaneously a specific astrophysical object with measurable properties and a potent symbol that engages our imagination and reflection. Its dual nature as both scientific subject and symbolic entity enables it to bridge the sometimes separate realms of objective investigation and subjective meaning. As we prepare to drift into sleep, let us appreciate this symbolic dimension of Cygnus X-1. Beyond its mass, spin, and orbital parameters, it carries meanings that connect it to ancient mythologies, philosophical traditions, and our own personal reflections on the visible and invisible, the known and unknown, the transient and the eternal. The swan in the night sky, harboring within its celestial form one of the most extreme objects in the cosmos, invites us to consider not just what we know about the universe, but what it means to us as conscious beings seeking understanding of our place within it. In our final chapter, we will bring our exploration of Cygnus X-1 to a conclusion, reflecting on the shadow that shines, the absence that reveals, this cosmic enigma that has expanded our understanding of the universe and our place within it. But for now, let the swan and its hidden black hole accompany you toward dreams, carrying symbolic resonances that have echoed through human culture, from ancient mythologies to the frontiers of modern science. Our journey exploring Cygnus X-1 has taken us across vast scales of space and time, from the early days of X-ray astronomy to the frontiers of contemporary astrophysics, from the formation of massive stars to their collapse into black holes, from direct observational evidence to the rich symbolism that connects this cosmic object to human culture and imagination. As we conclude, let us reflect on what might seem a paradox: how a shadow in space, an object defined by absence and invisibility, has illuminated our understanding of the universe and our place within it. Black holes are often described in terms of what they are not or what cannot escape them. They are regions from which nothing, not even light, can return to the outside universe once it crosses the event horizon. They are characterized by what we cannot see directly, by the signals that never reach us, by the information that appears lost to external observers. In this sense, a black hole is indeed a shadow, a darkness against the cosmic light. Yet Cygnus X-1, this cosmic shadow, has paradoxically been a source of intellectual illumination, revealing aspects of our universe that might otherwise have remained obscure. Through its discovery and continued study, it has shed light on the death throes of massive stars, the extremes of space-time curvature, the physics of accretion and jet formation, and the nature of binary star evolution. A shadow that shines, an absence that reveals, Cygnus X-1 exemplifies the often counterintuitive path of scientific discovery. This illumination extends beyond specific astrophysical processes to fundamental aspects of physical law. The existence and properties of Cygnus X-1 have confirmed key predictions of Einstein's general theory of relativity, providing observational support for this cornerstone of modern physics. The extreme conditions near the black hole serve as a natural laboratory for testing theories of gravity, challenging our understanding and pushing the boundaries of confirmed knowledge. What better test of a theory than its ability to predict and explain the most extreme objects in the cosmos? The apparent contradiction of a shadow that shines resolves when we recognize that Cygnus X-1, like all black holes, is not merely an absence, but a presence that profoundly influences its surroundings. While the black hole itself may be invisible, its gravitational effects on nearby matter and energy are dramatically visible across the electromagnetic spectrum. The X-rays that led to its discovery, the jets extending light years into space, the orbital motion of its companion star, all testify to the black hole's presence and power. This dual nature, simultaneously invisible yet influential, mirrors aspects of our own cosmos on larger scales. Dark matter, which appears to constitute about 85% of the material content of the universe, cannot be directly observed, but manifests through its gravitational effects on visible matter. dark energy, driving the accelerating expansion of the universe, similarly eludes direct detection while shaping cosmic evolution on the largest scales. Cygnus X-1, in its paradoxical nature, offers a microcosm of these larger cosmic mysteries. The journey of discovery that led to Cygnus X-1 also illuminates the process of science itself. From anomalous X-ray readings detected by early rocket flights to sophisticated multi-wavelength campaigns using advanced space observatories, the story of this black hole demonstrates how scientific understanding advances through persistent observation, theoretical insight, technological innovation, and collaborative effort across generations. What was once mysterious becomes comprehensible, not through sudden revelation, but through the patient accumulation of evidence and the continuous refinement of theory. As we've explored in previous chapters, Cygnus X-1 continues to challenge our understanding, even as it confirms fundamental physical theories. Its mass, spin, and orbital characteristics pose puzzles for standard models of stellar evolution and black hole formation. These ongoing challenges reflect the nature of science as a never-completed journey, a continuous process of discovery that revises and extends our understanding, rather than arriving at final, unchangeable truths. For those of us contemplating Cygnus X-1 from our vantage point on Earth, this black hole can illuminate aspects of our own existence and place in the cosmos. The atoms that compose our bodies were forged in the nuclear furnaces of stars, perhaps stars not unlike the progenitor of Cygnus X-1's black hole. When massive stars explode as supernovae, they scatter these elements into space, where they eventually become incorporated into new stars, planets, and ultimately, living beings. We are, in a very real sense, made of stardust, our physical existence connected to the life cycles of stars and their remnants. This connection extends beyond the material to the cognitive. The same human mind that evolved on the African savanna to ensure our ancestors' survival has somehow developed the capacity to detect, measure, and comprehend objects as extreme and remote as Cygnus X-1. Our ability to extend our understanding far beyond our direct sensory experience, to conceptualize phenomena at scales and energies vastly different from everyday human experience, suggests something remarkable about consciousness itself. The shadow of Cygnus X-1, 6,000 light-years distant, has been illuminated by the light of human intellect, our curiosity, creativity, and collaborative enterprise. This reciprocal illumination, the distant object revealed by human inquiry, while simultaneously revealing aspects of human potential, creates a meaningful connection across the light years that separate us. The black hole, in its seemingly alien and extreme nature, paradoxically brings us closer to understanding ourselves. As we lie here, drifting towards sleep, let us imagine once more the dance of Cygnus X-1, the massive blue supergiant star orbiting with its invisible companion every 5.6 days. Matter streams from the star toward the black hole, forming a swirling accretion disk that heats to millions of degrees, emitting X-rays that have traveled for millennia across space to reach our instruments. Jets of particles, accelerated to nearly the speed of light, extend perpendicular to the disk, interacting with the surrounding interstellar medium. This cosmic ballet continues whether we observe it or not. Yet through the tools of modern astronomy, we can detect, measure, and interpret this distant system, constructing a coherent understanding of phenomena far beyond our direct experience. This capacity for extended comprehension, this ability to make the invisible visible through inference and theory, represents one of the most remarkable achievements of the human mind. Cygnus X-1, the shadow that shines, the absence that reveals, invites us to consider both the vastness of the cosmos and the depth of human potential. As we conclude our exploration of this remarkable object, let us carry with us an appreciation for the enduring dialogue between human curiosity and cosmic mystery, between what we can observe and what we can comprehend, between the darkness of the unknown and the light of understanding. In the words often attributed to the physicist Richard Feynman, the first principle is that you must not fool yourself, and you are the easiest person to fool. The study of objects like Cygnus 10.1 embodies this principle, subjecting our theories to the rigorous test of observation, revising our understanding when new evidence demands it, and maintaining a humble recognition of the limits of our knowledge, even as we extend those limits. This intellectual honesty, this willingness to follow the evidence wherever it leads, illuminates not just distant black holes, but the path toward wisdom. As sleep approaches, let the image of Cygnus, the swan, gliding along the Milky Way, accompany you. Within its celestial form, invisible to the naked eye yet known through human ingenuity, Cygnus X-1 continues its cosmic dance, a shadow that shines, an absence that reveals, a reminder of the beautiful strangeness of our universe and the remarkable human capacity to comprehend it. It should not exist, yet it does. A shadow in the sky, brighter than understanding. Sleep well, under a universe still full of questions.